All right, welcome everybody to our February general meeting of the Central Florida Astronomical Society. I'm your host, Frank Kane, your president, such as it is, and welcome back. If you are watching this and you are not yet a member of the Central Florida Astronomical Society, what on earth are you waiting for? Here's some reasons why you might want to consider joining. You'll get access to our private events and dark sky viewing location out at Geneva, Florida, which we've been using much more lately because the weather's actually been cooperating a bit. Yay. Access to our Loaner Telescope program. You can contact loaners at cfas.org. By the way, if you're a current member and want to take advantage of that program to go borrow a C-Star or a new telescope or a mount or whatever you want to get your hands on and figure out what might work for you going forward. Also, our vibrant online community through the Groups IO platform. Quarterly meetings at the Seminole State Planetarium in Sanford, Florida. How cool is that? And we got one coming up next month. More on that later. Also, your membership includes Astronomical League membership, which includes the quarterly Reflector magazine. And you can feel good about it because we're a 501c3 organization, 100% volunteer powered. All of your money goes straight to our mission. Also, you get discounts on astronomy and sky and telescope magazines, which are excellent resources for staying up to date. If you're interested in joining, go visit cfas.org to see our membership options. Tonight's agenda, we're proud to welcome back Amy Oliver from the Harvard Smithsonian Whipple Observatory. Going to talk about the life cycle of stars. Following that, I got some club news for you that'll go real quick. And then special guest Richard Wright, our own member, Richard Wright, past president, is going to talk about his journey to bringing the new SmartEye product to market by Pegasus Astro. So that's pretty cool. And we'll wrap up, as always, with our Astrophotography Showcase. And we got a lot of submissions this week, which is awesome. So stay tuned for that. And with that, allow me to introduce Amy Oliver. Got a quick bio here. Amy C. Oliver is the founding director of Smithsonian STARS. That's Scientists Taking Astronomy to Rural Schools, a program of the Center for Astrophysics at the Harvard and Smithsonian. Public Affairs Officer and Science Center Manager at CFA's Fred Lawrence Whipple Observatory, and SkyNights Presenter at University of Arizona's Mount Lemmon SkyCenter. As an informal science educator and communicator, Amy works to bridge gaps in access to science learning opportunities for emerging and future scientists. She is principal scientific investigator on Dark SkyNet, a cross-border light pollution monitoring network, and Project GLOWworm, which found unexpected glowworms above 8,000 feet in southern Arizona. She holds a Bachelor of Arts from University of Louisiana-Lafayette, Master of Science from University of Oklahoma, and DEI certification from University of Wisconsin-Green Bay. Amy was elected as a Fellow of the Royal Astronomical Society in 2021, and currently serves as chair of the Tucson Pima County Outdoor Lighting Code Committee. Thank you so much for joining us, Amy.
Well, thanks for having me. Always fun to be here. Who was here last time? Oh, nobody can talk. We've muted everyone. It's okay.
Well, I try, but I can't mute
Anybody
them all.
who's out there who remembers the Astronomocato. That's the black holes where I got stuck in the cat.
Definitely. Oh, some quick housekeeping before you get started. If you have any questions, just pile them up in the chat, or if you want to ask them live at the end, you can use the raise hand reaction down at the bottom of the screen there. And do please keep yourself on mute during the conversation, during the presentation. Thanks.
Oh, hang on. I'm going to actually stop share for 2 seconds. I'm going to fix whatever I've done wrong over here. It's okay. We're all still learning how to use Zoom.
I'm telling you, they changed everything this week. Like nothing's where it should be.
Well, I couldn't advance the slides for a second there
Awesome.
on my own computer. So there we go.
Yay.
Now everything's back. You see everything now. Now I can advance slides.
Yes.
So pretty much everything Frank said about me is there yet again on this slide, along with some extra things. Frank made a joke earlier, if you weren't in here, that every time he talks to me, my job seems to get bigger. That is not inaccurate. He is 100% right. It always seems to grow, and it's going to just continue to get bigger, which is great news. And considering so many other things around us are shrinking or disappearing, it's always nice to be able to tell a group of science and astronomy affiliated individuals like yourselves that we are growing and we are continuing to go strong at the Smithsonian Institution. And if you need me for some reason, my email is at the bottom of this slide. So if you have questions after today, you can always email them directly to me. I'm going to be talking to you about 2 things today. First, I'm going to give you a primer to the Smithsonian Astrophysical Observatory's Whipple Observatory, and the Smithsonian Astrophysical Observatory that's where I work. and where I am stationed. And so we'll start there. I'm going to race through that because I really want to talk to you about the life cycle of stars. But I feel like it's always really important and kind of fun to just understand where we're coming from and what we're functionally doing and where we exist. So how this place started, the Smithsonian Astrophysical Observatory actually started and was founded in 1890 and became a formal partnership with Harvard College Observatory in 1955. And we took on a combo name in 1973, which is the Center for Astrophysics. So we just celebrated the anniversary of that, just barely in 2023. So we were really excited to be able to celebrate that 50th anniversary of just our name together. But Whipple Observatory, oops, and we're frozen. So there we go. Okay, so Whipple Observatory was founded in 1968 by Fred Lawrence Whipple. He chose our site in Amato, Arizona, high in the Santa Rita Mountains, which are what is in today the Coronado National Forest. We have over 30 telescopes on our site, and our site stretches more than 17 kilometers. So we're talking thousands of hectares of space. We're also at 2,650 meters in elevation at our highest elevation. That's about 8,553 feet. This is a really important location. If you know anything about Arizona and astronomy, it's, they sort of go together like peanut butter and jelly. And there's a reason for that, particularly in southern Arizona, which is where we have sky islands. So we have a very stable atmosphere because we get, minus more recent climate change events, very stable weather year round. And our sky islands then also take us high above the atmosphere, up into the atmosphere, not above it, excuse me, where we get less turbulence. We have less scintillation for stars. So we're able to study them with more accuracy. We often get confused with Kitt Peak, which is the National Observatory of the U.S. National Science Foundation. It's located about 2.5 hours away from us in Northwest Arizona, outside of Tucson, and we're to the south, so we're closer to Mexico. But we do very different work from them. So we're not doing even extraordinarily similar work in any way. Our site is heavily focused on exoplanetary research, studying stars and very violent activity in the universe. And Kitt Peak does other stuff. They're studying dark matter. So they have a DESI, they have WIN. So they're doing really significantly different work. At our site, we have these two cute little shoe boxes, or what's known as the Micro Observatory, which is a NASA project. Why there is a QR code on the screen is so that you can actually scan that, and then you can use the Micro Observatory network. I manage these on site, so I'm one of the technicians that takes care of these. You can tell these to take images for you, and we have these telescopes here, as well as there are some in the Southern Hemisphere and at Harvard at Cambridge, Massachusetts. And so you're able to take your own images and then we'll deliver them to you. So you don't operate these telescopes, but you put yourself in the queue and then they will take images for you of planets, nebulae, galaxies, and we're also now in beta for exoplanets. We also have a major science center. So one of my big projects was that I renovated this science center. It just reopened to the public in October of 2024. So this is the only Smithsonian museum located in a small rural community. So we're very proud of this and very proud of everything that we're able to do. It's extremely popular. We're getting like 300 people on an open day. It's a small space. That's a lot. We're often hitting fire code capacity. So we're very proud of that. We are also home to the only gamma ray astronomy array in the Northern Hemisphere. That's VERITAS, or the Very Energetic Radiation Imaging Telescope Array System. They are looking for the most violent activity in the universe. There are 4 12-meter optical reflecting telescopes at our site. Each one has 345 individual faceted mirrors on it and 499 eyeballs. What's interesting is if you have your cell phone right there anywhere, you have at least 1 million pixels in your screen of your mobile device. And these cameras only have 500 pixels in them. So we don't need to have elegance in order to study the most violent activity in the universe. We just have to be really precise. We operate on very long baseline interferometry, so those are connected through interferometry, and we are studying supernovae remnants, pulsars, globular clusters, active galactic nuclei, dark matter, black holes, and more. We also have the prototype Schwarzschild-Coude telescope for the eventual Cherenkov telescope array down in our backyard. So we're the spot that figured out how to build that thing. We built it, and now hundreds of them are being built between the Canary Islands and Chile. Up on our ridge site, which is at about 7,200 to 7,800 feet in elevation, we have optical reflector telescopes for solar system, galactic, and extragalactic astronomy. If you've ever heard of Juliana Garcia Mejia, she is a scientist from Colombia, and she's in charge of the Tierras Observatory for exoplanetary research. She is not only the astronomer, but also the engineer for the telescope. She built that on our ridge site. So most of what we are doing up there is studying stars, stellar metallicity, the birth and death of stars, and searching for exoplanets. Also at that same site, we have the M-Earth project, which is an array of 40-centimeter optical reflector telescopes that are used to search for exoplanets. M-Earth, so M-class planets. If you're a Star Trek fan, that's for you. We also have a collaboration on our site with Penn State, the University of Montana, the University of New South Wales, Caltech, and the University of Missouri, which is 470-centimeter optical reflector telescopes used to study exoplanets, and an additional red-based telescope. So all of those are also searching for exoplanets. That's called MINERVA, or the Miniature Exoplanetary Radial Velocity Array. So our red is our radial velocity. And we're almost to the end of all of our amazing telescopes, but these, which I call my very favorite shoeboxes, are actually a part of the Hungarian Automated Telescope Network, or HATNET. And you may have heard of HATNET because it is one of the most productive ground-based exoplanetary missions in the world. Has discovered more exoplanets and confirmed them than any other ground-based mission. And they are just 4 optical refractor telescopes with 200-millimeter lenses, and then 1 single reflector telescope. Part of what makes this so successful is that there are telescopes here and then also in Hawaii, so it never loses an eye on the sky. It's completely automated. They open on their own, they close for bad weather on their own, and we're just there to sort of help if something goes wrong. But these are extremely effective. They are also searching for variable stars, and they've been extremely effective at that as well. And then last but not least, certainly not least, is the MMT, which until 1996 was the multiple mirror telescope. But in 1996, we became the first telescope in the world to have one of Roger Angel's large-sized mirrors. We have a 6.5 meter mirror. My cat is in the back screaming up a storm, excuse me. And we, of course, love this telescope because it is the basis and a plot line to multiple other large-scale telescopes. The largest optical telescope in the world right now is the Large Binocular Telescope, and that is based on this model. The building, even how it turns, the way it plows its own snow, and the Giant Magellan Telescope is also based off of this model, off of the original MMT model when it had 6 mirrors. So we're very proud of this, and I'm going to show you a video to show you sort of what we're doing now, because Whipple Observatory is now old enough to be a historic observatory, but we are also still leading the way in all of the research that we do. We're doing a ton of spectroscopy here, but we're starting to lean towards something new. I'm going to quickly show you that video. Hopefully we'll have sound, and if not, because sometimes that happens in Zoom, we will bypass the video, but somebody, Frank or someone, shout out if you can't hear this video.
For millennia, we have looked up at the sky and wondered, what's out there? We now know that the universe is vast and growing larger, and is home to trillions of stars residing in billions of galaxies. But what if most of the universe was invisible? Scientists now believe that the universe is made up mostly of a mysterious, invisible substance called dark matter. But there's a problem. We have no idea what dark matter is. Computer simulations predict that our Milky Way galaxy is swarming with thousands of dark matter clusters, each millions of times more massive than our sun. The challenge for scientists is that dark matter clusters are invisible and so have remained beyond our reach until now. A team of astronomers is setting out to see the invisible and answer the question, what's out there?
So I'm super proud of this particular project. As you can tell, it's about dark matter, but it's a spectroscopy instrument. So it's a little bit different than we've been trying to look for dark matter in the past in a lot of ways. And if you're very interested in that, you can look up VIA spec. So that's a VIA spec. You can also look for the PI at Harvard and the Smithsonian. His name is Charlie Conroy. And you can learn more about this project that he's working on. He's building it now. It will go on the MMT. So we're very excited about that. And I wish I could tell you more about everything the Smithsonian Astrophysical Observatory does. And I just don't have time, but I am going to mention, we're working on a project called the Black Hole Explorer, which is a space-based component that will extend the capabilities of the Event Horizon Telescope into space. So we are going to further extend our eyeball and make it that much bigger. Plus we are working on NGEHT and adding additional telescopes right now, which is very exciting. So we have a lot of very cool things going on. And this is just a wonderfully exciting place to work all the time. And everything is going a million miles a minute. So we're very excited. But like I said, at Whipple Observatory, we work a lot on stars. So we care about the life cycle of stars. We care about how they are born, how they live, how they die, what they're made out of, and how that impacts our understanding of our own place in the universe, of our own place in our solar system. So today we're going to talk about, if I can get it to
For millennia.
Oh, no. Oh, there we go. Perfect. Okay. So we're going to talk about the lives of stars today. And I'm going to mention this a little bit right now. We're going to come back to this, and so I'm going to repeat this information, but you may or may not know that the Milky Way forms roughly 6 to 7 stars per year. And that's because about 4 solar masses of gas condenses into stars each year. And the average star that gets born is less massive than the sun. And the Milky Way star formation rate is low compared to starburst galaxies, which can produce tens or hundreds of solar masses of stars per year. But we're still doing pretty good. We are considered an active galaxy, and we're actively forming stars. And we are also the most active star-forming galaxy in the local group, which also includes over 100 nearby galaxies. So we have a very exciting little home that we exist in. And in our home, it's not just these outer regions that are forming stars. They're capable, but it's really our central region that is our star-forming factory. And that's pretty similar in a lot of ways to starburst galaxies and how scientists think about where stars are most likely to form. So about 1,300 light years away from our central supermassive black hole, that's Sagittarius A star, our star formation rates are 10 times higher than the rest of the galaxy. So remember I said we're forming 6 to 7 stars per year on average, and it's mostly occurring in that central region. And so that's why we're really talking about the life cycle of stars and what's going on, because it's happening right here in our home. So what is a star? And most of the time we all think we know what a star is. But, and of course I've got this cute little line on the slide, which is stars are huge balls of plasma that produce light and heat from the turning forces of gas inside their cores. That's a really simplified, but stars, they're not just glowing balls of light in the sky. there are 200 billion trillion stars in the universe. That's like 200 sextillion. I don't actually know how many that is, by the way. Someone's going to have to tell me how many elk that is. Because in America, we can measure everything as long as it's not imperial or metric. How many giraffes, how many elks, somebody figure it out. So the really crazy thing about all of these stars, though, is that we believe that most of these stars have planets. How crazy is that? And that even the new ones being born have that potential. It is absolutely phenomenal. And in just our galaxy, in just the Milky Way, we estimate that there are somewhere between 40 and 80 billion sun-like stars. Sun-like stars. So like our very own solar system. And about 1 in 5 of those, or 20%, are expected to have Earth-like planets orbiting them. So between 8 and 16 billion stars just in our galaxy. And remember, we believe there are 2 trillion galaxies. And we believe that these planets are just out there with Earth-like planets orbiting them. And to me, just right there, it's not even these crazy, beautiful images like this one of our own sun. This is a pretty good reason to learn more about stars. Because we think these things are happening out there. We are guesstimating based on all of the knowledge that we have that this is probably the truth. And we also study stars, by the way, because studying the ones that are younger than ours can tell us how our sun grew up, and studying the ones that are older or that have died can tell us more about what its life is going to be like. And 2, how long it will be able to warm Earth, which is our home. Oops. Sorry, we've got it. There we go. So I'm not going to ask you guys to actually answer this out loud because we have everybody on mute today, so I'll just go through it. But what are stars made of? Is it all the same stuff as Earth? Or fire and rocks? Nope, it's just mostly hydrogen and helium. But we know that they can't form without gas, but also without dust and gravity, right? All of these things are important to the formation of a star. So how long does a star like the sun take to form? Well, we know it's not instantaneous. We know it's not about 200,000 years. It's up to 10 million years. So despite the Big Bang sounding like something that happened immediately, that's not really how space works, right? And when we're talking on cosmological scales, they're much longer than the scales we're used to on Earth. 200,000 years to us sounds like a really long time, but it's like a drop in the bucket when you're making a star. In fact, it takes about that long just to accrete enough matter to start making the star. So it takes that long just to get the ingredients, basically. And it's about 1 to 10 million years, by the way, depending on who you ask. And that's because stars have to bake at about 10 million degrees Kelvin or 18 million degrees Fahrenheit in order to even start fusion. And fusion is required to make a star. And so basically what's happening is we have cloud disturbance in our star-forming factories or our star nurseries, which are our nebulae. And that disturbance in the interstellar dust clouds causes dust particles to start to clump together. And then we have gravity. Gravity pulls everything down, and the clumps start to grow large enough to have their own gravity, which then pushes inward on the star, or what will become a star, and it heats up its core, and then we go through nuclear fusion, and once the core is hot enough, then nuclear fusion begins and the star is born. Sounds pretty simple. It's just really much more complicated than I make it sound, and it takes a really long time. So in the simplest terms, which is honestly really what we have time for tonight, fusion is when two hydrogen atoms slam into each other and make helium. That's fusion. So we're going to talk a lot tonight about what are the stages of a star's life. And you can read up here on this slide, while all stars have similarities to each other, they don't all grow up to be the same. And the path they follow through life has a lot to do with how they start out. And isn't that interesting? It sounds an awful lot like people. And I have so many, dad approved star jokes about stars being so much like people. But what you're looking at, by the way, on the screen is visualizations of a high mass star and a low mass star. But we don't have time to just sit here and admire these or do all my dad jokes, which makes me very sad. So if you want them, you can email me back from that first slide again. We're going to go back to the beginning. So all starts in the nursery. At this visualization that we're looking at, and that is hopefully moving for you, it is moving for me, is a three-dimensional perspective of Hubble's image of nebula GUM-29 with the star cluster Westerlund 2 at its core. The flight traverses the foreground stars, so we're going through those right now, and it's approaching the lower left rim of nebula GUM-29. In a second, you're going to see that as we start to pass through those wispy, darker clouds, right about now, we're starting to go through those. On the near side, this journey, it's revealing bright gas illuminated by the intense radiation of these newly formed star clusters in Westerlund 2. And within the nebula, what you're seeing here along the bottom and up the sides is several pillars of that dark, dense gas are being shaped by that energetic light and the strong stellar winds from the brilliant cluster of thousands of stars. And this is where everything is being born. But what are they going to be? The simplest answer is a star. But will they be high mass or low mass? So while stars are born in these stellar nurseries called nebulae, they don't all just become the same thing and they don't lead out the same life. While the gas clouds collapse in and matter accumulates together to create a protostar, which is what you're looking at on the left, those later have to basically choose whether they will become a high mass star or a low mass star. It's a veritable choose your own adventure. So while our stars are living as a protostar or a baby star, they accumulate matter. And what determines the eventual life journey of our protostar is, and honestly, not to be glib, but it's time. Time and temperature. So what's really going on in this image here is that deuterium, which is an isotope of hydrogen, is burning. And that's really, really important. And most of us, we don't think about how important something like deuterium or just some isotope of hydrogen could really be. But in fact, it's, and I'm going to date myself, it's clutch. It's the reaction of the burning deuterium is what keeps the temperature inside that protostar a stable 1 million degrees Kelvin, which is just shy of 1 million degrees Fahrenheit, or 1.8 million degrees Fahrenheit, excuse me. And here is where our star chooses its adventure. So we're going to follow our low mass stars through their journey first and see what happens to them. The reaction of the burning deuterium that we were just looking at is, again, what keeps that protostar the right temperature inside at that stable 1 million degrees. So it's exactly like how my thermostat keeps my house at about 68 degrees. But if our protostar runs out of deuterium to burn, usually because it just didn't have enough nearby to collect in the first place. Its temperature starts to rise, kind of like if my thermostat breaks in the summer, or yours, you guys are in Florida, right? So hydrogen fusion, which is what creates a star, begins to occur once the protostar reaches 10 million degrees Kelvin. We already talked about that. So it's that 10 million degrees. And that's about the same temperature as Phoenix in July. And it's just shy of 18 million degrees Fahrenheit. So here you are looking at a star-forming region called S106. And somewhere in this beautiful image is S106 IR, which is a low mass star. Once that star reached its very high temperature, it stabilized and it became a young star. But it ran out of deuterium. So once it reached the peak of its deuterium, that is when it had to choose what kind of star it was going to be. And so remember, it's all about how much time does it get to stay at that temperature. If we run out of deuterium too soon, we'll become a low mass star. So once the protostar becomes a low mass star, it lives out its life in two primary phases. And those are what you're looking at right here. So that's main sequence, which is where the star... I like listening to myself echo. That was cool. So main sequence is where the star will spend about 90% of its life. And you can actually see these noted on the screen here. So if you're looking at those, you can see a main sequence star is roughly 0.08 to 10 solar masses. 90% of its lifespan is spent as main sequence. That's like the sun, Altair. Okay, so at this time, as a main sequence star, its composition is more than 98% hydrogen and helium. And 1/3 of its hydrogen is converted to helium. Main sequence stars, like I said, include the sun and Altair, and again, can be anywhere from that 0.08 to 10 solar masses, or that would be about 8% the mass of our sun to 10 solar masses, or 10 times the size of our sun. They can live for a very long time, but they have varied lifespans. Our own sun, for example, we estimate will spend about 10 billion years living as a main sequence star. So it is nearly halfway through its time as a main sequence star. And you could say basically it's entering midlife if we were thinking about human years. Now, after the star has lived for most of its life in the main sequence, it slowly transforms into a red giant. When it becomes a red giant, it will still maintain 99% of its original mass and will live out the remaining 10% of its life here at this phase. This includes stars like Aldebaran and Arcturus. And during this red giant phase, the star is expending hydrogen in its core, expanding or kind of pushing out its outer layers. And during this time, it can also grow more than 100 times the size it was as a main sequence star. So what you're looking at on the screen is not to scale. But because these stars keep expanding and extending their outer layers, eventually the outer layers of gas are ejected while the star core contracts. This is a process that then goes on for tens of thousands of years. And that's much shorter than the previous periods of the star's life. So if you think about it, billions of years to get to this point, and it's just a blip of the radar, in fact. So here we're looking at M57, or the Ring Nebula, which is a planetary nebula. And this is a misnomer. I'm sure all of you know this, because a planetary nebula actually has nothing to do with planets, although they can be very large in size. In fact, the Ring Nebula is about 1.3 light years across. That's nothing to sneeze at. To give you some context, if we were on the Space Shuttle Discovery and positioned down there at the left, lower left dot, and we wanted to get to that upper right dot, well, the Space Shuttle Discovery can go about 5 miles per second. That's 18,000 miles per hour. And at that speed, it would take us about 48,360 years to cross the Ring Nebula. That's pretty big to us, but it's pretty small on cosmological scales. And of course, today we're not just talking about distance, we're talking about mass. Planetary nebulae are so small that they're just about 0.1 to 1 solar mass. They're not very dense in relationship to stars. The total mass of the Ring Nebula is estimated to be at about 0.62 to 0.65 solar masses. So a little over 65% of the mass of our sun. So after this, right, we go, oh, what happens after a planetary nebula? So while a planetary nebula, the star's core is still continuing, for the most part, to contract and compact down into a type of star known as a white dwarf. And these stars are very low in mass, in fact, just 5 to 15% of the original mass of the star. So if you think about that, imagine those stars that were just 8% the mass of the sun, and then what that means. We call these extremely low mass white dwarf stars. And in fact, as of right now today, my colleague Warren Brown at the Center for Astrophysics has cataloged the most extremely low mass white dwarf stars ever to date. And that's just about 100. Actually, I need to do a follow-up with him because he may have found some more. But when the Vera Rubin telescope goes online, so this summer is the projected new date, Warren estimates that we could find many more than what he's found in a career in just 1 hour. So we could find 100 of them in an hour, and it's taken him a full career. Maybe even a minute. He doesn't know, but he's excited. And that's the importance of continuously upgrading our technology and getting better at what we do. We can see things we just couldn't see before, detect things that were hiding in plain sight. Eventually, you figure out questions we didn't even know we had. But I'm getting off course because I get too excited about what Warren does, and because I got to write all the press releases for these things when he did them. But eventually, the planetary nebula that's surrounding this white dwarf, or let's just say the Ring Nebula, right, will dissipate. It'll go away and it'll leave behind just the white dwarf, but they can and do exist at the same time. So I want to make sure you understand that. Remember that the nebula only lasts tens of thousands of years, and the white dwarf can live much longer. In fact, scientists aren't even 100% sure, but estimate a white dwarf could possibly live up to a quadrillion years or longer. Yet another number that I'm not sure how many elk that is. But the reason that we're saying what we do is because the oldest stars in the universe are still pretty young on this scale. And so there's a lot that we still don't know and that we haven't learned yet, and a million questions that we still need to find the answers to. Maybe Vera Rubin will give us some of them. So what happens after a white dwarf? We don't know. We don't know. Lots of question marks here. So scientists have hypothesized that what happens after a white dwarf is a black dwarf, which would be a cooled off white dwarf. However, the universe's existence is too short. In other words, the universe is too young yet for us to prove this theory, or we just don't have the tools yet to figure it out. That's just like it taking many decades to find extremely low mass white dwarf stars. We need that better technology to find out what's out there. Look at how small they postulate the largest of these objects to be. That's up on the screen. That's less than 1.4 solar masses. We don't even have a starting point or a benchmark for this. And so we can sit here and maybe tonight we could debate, why do they come up with this if they don't know that it might be out there? And that's theoretical physics. Somebody has to come up with a theory based on the knowledge that we have. And then we go out and we use the tools that we have, or we create new ones to prove or disprove that theory. And you'd be surprised how many times our theoretical physicists are dead on. And maybe, again, the Vera Rubin will give us that, or maybe the Giant Magellan Telescope or one of the ELTs that will come online. We could be right or we could be wrong. The thing is that everything in science starts as a theory. It starts as a hypothesis. We have a question, and again, we have to go out and find the answer. And that's what is so cool about what we do. So meanwhile, back in the nursery, right, there's all these other stars hanging out. And I'm not going to let this roll back through, but I know you guys remember we were passing through this nebula and getting to Westerland 2. And so every nebula can have multiple star-forming regions. And each of these regions can create thousands of stars, usually in groups or clusters of up to 3. And sometimes due to stellar and other winds or other activity in the nebula, these stars can become spread out, like you're seeing here. The larger a nebula and the more active its star-forming regions, the more stars they are poised to make over their lifetimes. A particularly dense nebula with a lot of gas and dust that is very large, like the Pillars of Creation, the Eagle Nebula, produced some 8,000 stars, more than 5.5 million years ago. And remember, these nebulae are in our galaxy, which consists of about 100 billion stars. So our star factories have been extremely active, very, very active. But we're not even the most active. The largest observed galaxy in the universe is IC 110, and it has an estimated 100 trillion stars. So what happens when we have enough time to burn deuterium and we have a bunch of stars and they're all hanging out and they're having a rave is that deuterium sits for longer. We have enough to keep burning. We reach our stable temperature of 1 million degrees Kelvin, and then we have enough time to reach 10 million degrees Kelvin. And the longer that deuterium burns and keeps the protostar at a low temperature, the longer it remains a protostar, and the more time it has to accumulate mass, thus becoming a massive star, if that makes sense. So the deuterium is there to keep that temperature stable so that this star can go from itty bitty to very big. Here we're looking at L1527, which is embedded within a cloud of material that is feeding its growth. So ejections from the star have actually cleared out the cavities above and below. If you think about that and you think about the art that I showed you earlier of a protostar where it was making ejections and they were triangular in shape going up and down, that's perfect. It's a perfect match. And the boundaries here are actually growing that glowing, not growing, excuse me, that orange and bluish look to them. And this is an infrared image from NASA ESA Space Telescope. The upper central region that you're looking at here looks kind of like a bubble, and that's due to stellar burps or sporadic ejections of material. So that's why you're seeing that sort of bubble shape coming in. Now, once a protostar with high mass becomes a stable star, after a very long time, it too lives out most of its life in the main sequence, just like a low mass star, followed by a very short time as a giant or supergiant star. So you can see it's almost identical how they go through those phases. But just like our low mass stars, more than 98% of the composition of high mass stars in main sequence is hydrogen and helium, and roughly a third of its hydrogen has been converted to helium through fusion. It's sort of amazing, the analog between the two. But you'll want to notice that the red giants of the low mass star life cycle were barely reaching into the mass of the main sequence here. So our red giants of a low mass star were barely at the low end of the size of a high mass star in its main sequence. That is crazy that they're capping out at 10 solar masses, and here's this main sequence star, and that's a baby star in terms of size. So when these massive stars enter the final 10% of their lives, their giant or supergiant phases, they actually start to lose significant amounts of mass, and that's where things start to get different. It's like a crash diet. But they also start making heavier elements, which is something new and different, like iron through fusion. So remember, while our low mass stars can live for billions of years, our high mass stars, they're not living quite so long. They've lived large and in charge and have been quite gluttonous. In fact, the more massive a star becomes, the shorter its lifetime. And that might be surprising to think about. The bigger it becomes, the shorter its life. Stars between 10 to 15 solar masses are believed to live just about 10 to 20 million years. At those that are the most massive, say 150 solar masses, are believed to live just a few million years. This happens because they run out of fuel faster than their smaller counterparts. So if you think about vehicles, a smaller vehicle is usually more fuel efficient than a big heavy truck. And as these stars continue to fuse heavier and heavier elements, they become less and less fuel efficient. It's exactly the same. As a very massive star becomes less fuel efficient, it can collapse and explode outward, or just explode outward. Its outer layers of hydrogen and helium are ejected along with some heavier elements the star had been producing. And here's where we're looking at Cassiopeia A. Of course, Kepler supernova is also a good example of this happening. And here we're looking at a zoom into Cassiopeia A from the James Webb Space Telescope. It's absolutely gorgeous. But when a star explodes in this way, it is so powerful, it creates atomic nuclei. It creates its own structures, which you can see here. And in a lot of ways, it becomes its own little world. Just looking at the remnants of Cass A, it's so clear that there's a lot going on here. And it's very exciting to study and even just look at this. It's a very active region. That sometimes the explosion can be so big that the star dissipates into a diffuse nebula, but a lot of times the death of a star is so violent that the core of the star collapses back in on itself, and one of two things happens. So when the core collapses, it's a little bit like a horror movie. You know, when the people split up and some of them go into the basement and some of them go into the shed in the woods. And you know nothing good is going to come of either decision. In the case of a supernova, what comes after is usually a black hole or a neutron star, depending on the level of violence of what's happening around this area. So when a star collapses into dense matter, it can become a black hole, which is a very violent celestial object that you're very familiar with. I know that shreds light and matter, and nothing can escape its gravitational pull. And although it seems so small at just 3 solar masses, in some cases, even those very small black holes are gravitational monsters. And don't think that means that they're all small, by the way. There is a black hole so massive that scientists had to come up with a new term to describe it. Ton 618 comes in at 66 billion solar masses. So now here we're looking at M87, which is a new image of the first black hole that was ever imaged, newer image. It's about 8 months old. So M87, which was the first black hole ever imaged, comes in at about 2,400 billion solar masses. So, or not 2,400 million, excuse me, solar masses, which is just absolutely dwarfing our own supermassive black hole. Sagittarius A star is just 4.3 million solar masses. As if that's not enough, the other possibility is that the star's core collapses into a dense mass of neutrons. And you think, well, it's just a star. But neutron stars can be dangerous. They have a lot of mass in a very small space. And if one came into our solar system, which is not going to happen, I assure you, the resulting chaos would throw planets out of orbit and raise tides on planets and moons to the point they could rip their own planets or moons apart. But let's be clear, the nearest neutron star is causing havoc about 500 light years away, so we have nothing to worry about. In the case of Cass A, that supernova remnant, there is a neutron star in Cass A. At the time of discovery in late 2009, it was the youngest neutron star ever recorded by astronomers. So we know that it's there and it's wreaking some havoc. And then, of course, it all ends back in the stellar nursery. So stars explode, particularly in the case of like Cas A. They create clouds of gas and dust, which can then collapse in on themselves, clump together and form new stars. That's why when we look in the regions surrounding Cas A, we're also seeing potential star formation and actual star formation. It's because it all just comes back together. It's this sort of macabre but very beautiful cycle of what is happening in the universe and how it continues to sustain itself. And so the last thing I'm going to show you before we are maybe, there we go, is just sort of the map we have followed together tonight to get through the life cycle of stars. And I will open it up to questions.
Thanks so much, Amy. That was awesome. Yeah, so if you have any questions, pop them in the chat, or if you want to ask live, hit the react button down at the bottom there and hit the raise hand icon, and I'll call on you. We do have couple of questions coming in already, but I'm going to abuse my privilege as host and ask one of my own. So we often hear that all the heavy elements that are on the Earth, like gold and everything else, are born of supernova explosions. I just want to fact check that. Is that true?
All types of heavy elements can come out of a supernova explosion. It sort of depends on what the star was made of to begin with. And, I'm sort of pseudo answering your question, but I think it's important to sort of go back to why we study what we do at Whipple Observatory, which is stars can have all sorts of things in them. Sulfur, magnesium, carbon, all different sorts of things, and what's being fused. And so it's not necessarily going to happen with every type of supernova explosion. They all explode something different. Does that make sense?
Mm-hmm.
And it sort of depends on what was in there to begin with, because science is not alchemy. I can't make salt into wine, and I can't make salt into gold, but give me enough of all the things that could potentially fuse down together, and we'll see what happens. So yes, that's how elements are made, is through fusion, and through things fusing together, and then explosions happening, and then new elements fusing together are being created.
Cool. We are all made of star stuff, as they say.
Yeah, everything's made of star stuff. I mean, except for the elements we made in a lab,
Awesome.
which are probably also still sort of made of star stuff.
Indirectly, yeah. All right, well, you sparked a lot of imagination here. We got a bunch of questions here. Bob asked one that I have as well. Going back to that small imaging telescope service that you showed earlier on with the QR code. What does that cost? That sounds kind of awesome.
It's free.
Free?
Scan the QR code. Hang on, and use my babies for free. Can I get back there? Let's see.
I actually pulled it up on my phone. Yep.
Micro Observatory is free. It takes about 2 days to get your image once you're in the queue. And then you can use, J2000 or whatever you're using at home to process your images. And yep. And you're sort of limited because we can only let you take images of things we can actually see from our observatory. So keep that in mind. And we have a mountain in the way, so don't pick anything directly to my east. But until it's like high overhead in the nighttime. But a very large mountain. So, but yeah, it's completely free, and we encourage people to use it. Actually, right now, if you don't mind my stumping a little bit for the University of Learning, they're doing a project right now that is a contest. So you use images from the micro observatory, or you take your own images with micro observatory, and then you process those, and then you submit them to the contest through the University of Learning.
Very cool.
But this is always free. So Micro Observatory has been at our site a long time. It'll continue to be at our site, and we're actually looking for ways to expand it right now so that we'll have even more options on the sky.
I somehow never knew about that. That's awesome.
I'm sorry.
We'll keep it a secret. We don't want too many people to know about it, because then there won't be any capacity. But
no, we want everybody to know about it, because the wonderful thing about, when you say then we won't have any capacity, the thing about this kind of program in science is that when we have enough demand, it makes it easier to expand.
Okay.
So it's not, demand equals a longer queue, it's demand equals expansion.
All right. Well, you can expect some demand from us, I think.
Great.
That's awesome. Jeffrey Martin, I'm going to kind of paraphrase your question here. I think he's basically asking, given that the universe is only 13.5 billion years old, how do we know that white dwarfs last that long? Trillions.
We don't, right? We don't. That's a great question. And that goes back to the universe is so young and we are still relatively technologically young that there's two things kind of standing in our way. That's why we have theoretical physicists. They tell us, based on everything we have learned so far, this is probably what's going on. Now go out and figure out how to prove it. And then our job is to figure out how to prove it. And if we don't have the tools to prove it now, we got to figure out how to build them.
Yep. Fair enough. Oh boy. William Castro has a few questions. I'm going to kind of bop between people here just to be fair. So let's start with this one. What percentage of stars are multiple star systems? And are there any multiple star systems with exoplanets?
Yes to the second question. To the first one, I actually don't know the answer to that. I don't know how many multiple star systems there are. Part of the problem is that I swear they find more of them every day. So I don't know the answer to that. I actually there was a young scientist still in college. She's still in her undergrad, just found a bunch just a couple weeks ago. And there were a number presented at the AAS conference in January. So I just truly don't know the answer to that. This is sort of like asking people how many moons Jupiter has. Today, how many does that have today? But yes, to your second question, a firm yes, we do know that there are multiple star systems that do have planets. And that young woman I'm talking about, her last name is Dunning. She has discovered some of those herself. Multiple star systems that have planets in them.
Cool. I'm going to hop over to Luke C here, who asks, is the dividing line between high and low mass determined by back calculating whether the star will end in supernova or planetary nebula?
That is an interesting question. Determining whether it's going to be low mass or high mass is about stability of temperature. So it's how much deuterium it has to keep it at that stable 1 million degrees in its core for a longer period of time. And that's what the primary determining factor is. So if it has less deuterium and it burns off quicker, it's going to become a low mass star. If it has more deuterium and it can stay burning and stay accreting matter for a longer period of time, it's going to become a high mass star. So it's not really about back calculating. It's all about the deuterium.
Gotcha.
I need to make that a t-shirt. That's all about that.
All about the deuterium, not the base.
That's exactly where I was going. Thank you.
Yes. All right. Wesley Clem asks, you listed that neutron stars have a lifetime. Is that due to mass and energy loss? What's causing that?
I'm going to slide back down there so we can actually look at maybe not. Hang on. Here we go. So that is what we think. So again, look at that number, right? And that number, if you're looking at that 10 to the 70 of a black hole and 10 to 45 of a neutron star, we haven't quite been alive long enough to have figured out the answer to that. So I hate always saying I don't know the answer, but I don't know the answer because we don't have an answer, which is a great reason not to know the answer. Stick a pin in that, and hopefully when the Vera Rubin turns on, I'll be able to answer that question for you.
Awesome.
We're a little shy on the technology to answer your question, and it's a really good one.
Excellent. Do you have a hard stop at 8, or can you take a couple more?
No, I'm fine. Whatever
Awesome.
works for you guys, because this is your meeting.
Thank you.
And it's not 8 for me, it's only 6 for me.
That's right. Must be nice. All right, going back to Bill Castro. He often gets asked at outreaches how much additional mass would Jupiter need to become a star? I believe this comes from the belief that people have that Jupiter is a failed star. What's your take on that?
Hang on. We figured this out at Mount Lemmon in elk. Which is funny, and everybody keeps laughing, but how many elk did Tommy Solansky decide we needed to turn Jupiter into a star? Too much.
Yeah, it's actually pretty far short if I remember right.
Yeah, it's, I mean, hang on, I have this note. Hang on. I know that he did this. All right. I'm gonna not tell you how many elk it is, but I know that he figured this out. Hang on, I'm just WhatsApp him and be like, answer the question.
Phone a friend.
No, okay, I found it. So Jupiter is only 1/1000th. It's a little less than that actually, but it's about 1/1000th the mass of our sun. So it would need to be 1,000 times more massive, basically, to become almost the sun. But essentially, if we were to ever figure out, right, so there's a belief that Jupiter is a failed star, but if it was, and it ended up turning into a planet, which is sort of awkward. I don't know that necessarily could happen, but again, we're still learning about planetary systems around other stars, to be able to know if that has happened anywhere else. But it would have needed a lot more deuterium, right? I keep going back to the deuterium because that's what it is. But essentially, a planet forms in a little bit different way than a star. So the likelihood that it was just a failed star, maybe, but it would need to be 1,000 times more massive. But we would need to know how much deuterium it had for me to tell you if it was possible, because it's not just about mass. It's never just about mass. The creation of a star is always going to come back to whether or not it could complete fusion.
And that's actually a great segue to Luke's other question here, who asks, if deuterium fusion is the first part of star formation, how did the first stars in the universe form before deuterium had been formed? Ooh.
Oh, that was a really good question that I don't know the answer to. Because our standard basic belief is that, actually, I do know the answer to that. Deuterium is an isotope of hydrogen. So it's not a standalone element. And so essentially what you're looking at when we say, well, before deuterium had formed, hydrogen was there. So at the Big Bang, we had the essential product for deuterium. So that isotope just breaks off as things break down. So those first stars would have had deuterium. It was already there.
Right.
And so, once you have that base element, you've got the isotope. It just hasn't broken off yet.
All right, hopping back to Bill, is there any way of determining the orientation of the axis of rotation of a white dwarf in a planetary nebula? Say for M57 or M27.
Yes. Actually, yes, and I know exactly the person who's going to do that. The name of the guy who's going to figure that out someday soon is Sebastian Gomez, and the Vera Rubin. I mean, I hate to say that, but right now it'll be the access point for them to actually do that work in a meaningful way will be the Vera Rubin or an ELT telescope like the Giant Magellan or the VLT or something that's coming online. And the reason that we need that is because we need more samples of them. So particularly, let's talk about those extremely low mass white dwarf stars that are out there. 100 is not enough. We need, 10,000 of them to do a meaningful sample, and that would be the same. So then we need to find 100,000 more nebulae or supernovae to figure that out and then bucket them down. And then we get into a conversation about AI and using AI co-pilots to help us do that. And that was why years ago I created, Tinder for spectra, because, and that sounds super funny, but it was swipe right for interesting, swipe left for, something we've already seen before, just to teach the AI how to bucket things out as interesting or not interesting, because we don't have enough astronomers to do what you're asking about right now in a meaningful way, because we need so many samples. We don't have enough people to actually go through the samples to do that math, because we have to narrow it down first. And so we have a lot of work ahead of us, but the answer is yes, there is a way to do that. I know who's going to make it happen. And we need AI, which Cecilia Garofalo is making happen, to do that kind of the lengthy part of the work, so that the guy with the brain can figure out axial movements and tilts.
You have the coolest friends.
I do. I have the greatest friends.
All right, I'm going to wrap up with Saad, who just has some kind words here, and maybe some food for thought here. She says, that was a great presentation. I don't have a question, just a comment. I find it fascinating how stars go through cycles of birth, death, and rebirth, just like concepts in Eastern Vedic philosophy, where the universe is believed to collapse and regenerate endlessly. So kind of cool how there's some ties to ancient traditions there going on.
Yes, very, very cool. I think you would find that that's true across many cultures. As I get more involved in tribal nation work and understanding tribal nations and indigenous cultures. I just spent a week in Hawaii learning about their culture and their connection to the stars and the things that they know and how it connects back to the universe and to the cosmos in these really beautiful ways. I'm like, wow. And these are traditions that have been passed down for generations upon generations before astronomy was even formalized. And I think, isn't that amazing that they already knew this, but they hadn't even seen a planetary nebula in that way, but they knew.
Yeah.
And so it's a very interesting and very beautiful. And thank you for saying that. It's nice food for thought for everyone.
Absolutely. Got a couple of other kudos from Bob there. Thanks you for the outstanding presentation. Very interesting and informative. And yes, Bob, we will make the It's All About Deuterium t-shirts happen somehow. Thank you so much, Amy. That was awesome. I'm going to let you get back to your evening, or if you want to hang out with us and geek out, you're welcome to. But
no, I'm going to go write a press release about the STARS program.
All right. That sounds more important. So we'll let you go. Thanks so much again, Amy. Always good seeing you.
You too. Bye.
And with that, I'm going to share my screen and get back to club news. There we go. I think I did that right. All right, yeah, so lots going on still. I know we just did this a couple of weeks ago, but yeah, there's still new stuff going on. We have more Geneva Dark SkyNights coming up. February 21st, 22nd, and 28th, as well as March 1st are on the docket. So keep your fingers crossed for clear skies. As always, keep an eye on the group's I.O. community for a last-minute word on whether we're going to actually open up that night or not, based on the weather forecast and availability of people to open the gates and whatnot. But hopefully we'll get some more observing in there before the summertime clouds roll in. Also coming up on April 17th and also extending into the 18th, I believe, we have our exhibit at the Orlando Museum of Art coming up. How cool is that? Again, the deadline for submissions is February 28th. That is kind of a little bit close for getting things printed up and delivered to the museum in time for them to get it all together. So I would encourage you to get that in sooner rather than later if you're still waffling on if you want to submit your stuff for display to the Museum of Art. There is a judging process that goes through. You know, we need to make sure we can't show everything, unfortunately, but we will pick the best of our submissions and get them up there for the world to see. Again, this is at your own expense. So, you do need to cover the cost of printing. We need something that's ready to hang, basically. We'll give you more details once we get your submissions, though. However, you are allowed to sell your items at this event. So if somebody wants to buy that print from you, maybe you could even make a few bucks, unless you're on the board of directors, because we have conflict of interest policies. So do get that in, and that will be a fun event for all. Mark your calendars for April 17th. We got quite a bit planned for that. And our next meeting is going to be in person at the planetarium on March 15th. So I'll see y'all live there, 6 p.m. at the planetarium at Seminole State in Sanford. Our own Derek Demeter will present a program on women in astronomy in the planetarium dome. And we have a whole bunch of breakout rooms lined up for you. So more details coming out in Groups.io. In fact, you can see it now in the calendar on Groups.io if you want more detail on that. And following our March meeting, our next Zoom meeting will be on April 9th, featuring someone else from Harvard, Dr. Avi Loeb. He's kind of a celebrity in the field of astronomy. He's in charge of the whole shebang there at Harvard Astrophysics. And he's made some pretty controversial claims. You know, his kind of claim to fame is investigating whether or not there's alien technologies out there and maybe even aiming some curiosity at our own little star system. Maybe they're lurking in our solar system. We don't even know it. He has some evidence, so let's hear him out. You know, we'll see where that goes. His whole thing is basically he's trying to encourage people to look into these big questions that have been kind of like shunned by academia in the past, and he wants us to be a little bit more brave. So I'm looking forward to that talk. It's going to be interesting for sure. Also, our outreach calendar is packed still. There is just a ton of interest in astronomy lately. We're seeing this in our membership as well. Like we're just getting all sorts of new members coming in lately too. So it's great that we can like provide this sort of opportunity to look outward and look up and kind of like get a broader perspective on the universe here and share that with people. If you want to get involved, head over to cfas.groups.io/g/outreach and join our group there to get notifications of upcoming outreach events. I saw some Science Night Live ones getting posted today. Or you can just contact our outreach chair, Doug Woods, at outreach@cfas.org. Always a great thing to get involved in. It's a very rewarding thing to do, to get out there with a telescope, show kids Jupiter for the first time, show them Saturn for the first time. You can change their lives for real. It's a very great thing to do. And even with adults, you know, you can open their eyes as well. So thank you to all who participate. There's too many of you to list, but you know who you are. If you're out there doing the outreach circuit, thank you so much for all you do. And you're really fulfilling the mission of this organization more than anyone, except maybe our Lonerscope chair. That's pretty cool too. And our Lonerscope program does continue to expand. A reminder, we do have a C-Star in stock now too, for all you who are C-Star curious. And we've got quite a bit more inventory lately too. And we just keep getting more and more donations to the club, and that makes us happy. So whatever kind of telescope you're interested in, whether it's a Celestron or a Dobsonian or a Newtonian, we got them. So just contact Christopher Hunt if you want to learn more at loners@cfas.org. And thank you, Christopher Hunt, for all you do in that program. Recently, a huge effort to move all of our stuff to a new storage unit, by the way. And I just can't thank everyone enough who was involved in that move. Also, welcome new members. Again, we're getting a lot of them this month. So thank you. Thanks for joining us. Welcome. And by the way, if you're at the in-person meeting in March, say hello. You know, I'll ask you to raise your hand. And if you want to introduce yourselves, you can. You don't have to, but we're always happy to meet new people. Do make sure you read your Welcome to the Central Florida Astronomical Society letter that you got with your membership. Lots of important information in there, including how to access our community platform on groups.io. That's how you're going to learn about all of our events that are coming up and how to participate with all of our various programs. And it also explains all of your various member benefits, like the loaner program I just talked about. So do double check that letter. There's lots of good stuff in there. If you still have questions, feel free to contact our board members at large. That's Wes Clem and John Pinto. They can be reached at bmal1 and bmal2@cfas.org, or you can talk to me too. You know, I don't bite. President at cfas.org. My name is Frank. And speaking of the board, we're always looking for new help. So we are in need of a publicity chair. Right now, people usually find CFAS through our website or through our outreach events. We don't do a whole lot of actual marketing or publicity. And if that's your thing, if you like social media and stuff, let me know. We could use your help. Or consider serving on a committee. You know, even though we have committee chairs in place for most of our committees, we can always use an extra hand. You know, we always want to make sure that we have, more than one person that knows how to do important stuff. So, we want to make sure that's in place. So if you are interested in serving, either as a Padawan learner or as a committee chair, the various committees include education, events, programs, outreach, loaner program, treasurer, science committee, website committee, membership committee, observing committee, or you can even make one up. But we'll take all the help we can get. So if you are interested in volunteering and getting more deeply involved behind the scenes of CFAS, do please let me know at president@cfas.org. And finally, another reminder that we are a charity, and any donations you make to CFAS, including your membership, are tax deductible. That also goes for any equipment donations you make to our loaner program. So if your tax plan includes charitable donations, remember, We count too. You can click on the donate button at cfas.org if you want to make a cash donation, or just contact us if you want to donate equipment or anything else. Also, if you're at Disney or any other organization that participates in cyber grants, that enables matching donations, and we are listed in there as well. So you can double your impact by using cyber grants. Upcoming astronomical events. Tonight's a full moon. Boo. Oh, unless you're looking at the moon, but even then, it's not a great time to look at the moon. So, well, we'll kind of get some narrowband data if you can. That's about all you can do in a night like this. But however, there is kind of a cool thing. The full moon and the star Regulus are going to be within about a degree of each other. So go outside of this after this meeting, look up. You might see a little pairing there of the full moon and Regulus. And that's kind of the theme of the astronomical events in the coming month. It's the moon with some other bright star getting like freakishly close together. This keeps happening. On the 17th, for example, the moon and Spica will be within 1 degree of each other. And on the 21st, it's going to be the moon and Antares. So it's just kind of a parade of the stars of the night sky, if you will. Oh, pun intended. Another cool thing is on February 24th, Venus and Mercury are going to be right next to each other, right at dusk. So catch that right as soon as the sun goes down. They won't be up there for long. They slip below the horizon quite quickly. March 9th, daylight savings time begins. Boo. We have less nighttime. That's not a good thing. But don't remember to adjust your clocks there. But the cool thing, on March 14th, we have a lunar eclipse coming up, a full lunar eclipse. So how cool is that? Get out there. The bad news, though, is that it's between 1 and 3 a.m., but it is on a weekend, so who needs sleep, right? Also, as lunar eclipses go, it's not an awesome one. It's kind of the shadows hitting the moon at kind of an angle, so it's not going to be like a really deep red, blood moon, if you will. But, it's still a lunar eclipse. It's still going to be awesome. It's always fun to watch. So if you are able to stay up from 1 to 3 a.m. and the skies cooperate, definitely worth getting out there and watching and maybe even photographing. Also, just more generally, the planets Jupiter and Mars remain well positioned all throughout this coming month. So if you're looking for something to take a quick look at outreach, those are great targets right now still too. They're going to be high in the sky and still pretty close to Earth. So they're going to be a good target to look at. And we're starting to get into the galaxy season for deep sky objects. So we're still in a period where the Milky Way is above the horizon, right after dusk for a few hours. But when you get into the wee hours of the night, the Milky Way is already gone. And as we get more and more into the spring and summer, you're going to be more into looking at galaxies that are outside the plane of the Milky Way. So when we look at all these beautiful images of nebulas, those are all inside the Milky Way itself. And when the Milky Way sets, all you're left with is stuff outside of the Milky Way, which is generally other galaxies. For example, this is an image of Bode's galaxy, M81. It has a friend called M82, which is a starburst galaxy that we just talked about. And some other good targets, the Whirlpool galaxy, M51. M106 is a favorite of mine, and M101, the Pinwheel galaxy, also good targets as we get deeper into spring. So that's the club news. And with that, I'm going to hand it over to our very own Richard Wright, who's going to talk about the story of his new baby. Richard, are you there?
I'm here.
Awesome. I think
Can
you
you hear
have
me?
co-host privilege. Yes, yes.
Yes.
And
All right. So
I will stop my
let's.
share.
Okay. And I'm going to share this screen. And yes, I'm going to allow Zoom to do whatever it wants to do. Do, do, do. Nothing like being prepared. All right. So I'm going to talk about SmartEye, the world's
Hey.
first smart eyepiece, and my journey and how it came to be. So, there'll be a little commercial at the end, but if I kind of want to know, well, anyway, here we are. So, all right. So in the beginning, so to speak, where did I come from? I was a computer graphics specialist for the much earlier in my career. Lots of cool 3D stuff. You can see here, I'm actually the co-inventor of the Tesla Cyberplane back in the mid 90s up there. So, I wrote some books on 3D graphics, and that was really great. And so, I made a name for myself in that career. And, I was pretty much a nerd with the telescope. Oh, I forgot to press that button so you can see the cool animation. So, just for a long time, I was just a nerd with the telescope. I've been an amateur astronomer for a long time, and I put a DSLR on, actually, it was even before this LX200 here, and started taking pictures of the moon and things like that. And I started my own side gig while working, as an engineer, making software. I like making software and creating products. I did a weather package and a couple little astronomy doodads, but I really, really, really wanted to make astronomy software. And so my big break came in 2002, which was a really long time ago, and if you think about it. And I worked on Starry Night version 4. They were looking for an OpenGL expert. Hey, I know a lot about that. And well, do you know anything about astronomy? Well, I've got a telescope. Actually, I had a couple telescopes at that time. So like, great, graphics, telescopes. You can come and work for us. And that was great. About less than a year later, however, I got laid off. It's the only time in my entire career, even to this day, that I ever lost a job. It was, the space.com, the bubble burst, and all that sort of thing. It's complicated. But the people I worked with at Starry Night were really great, and we became friends. And we stayed friends for like 20 years. We stayed in touch with each other, which is going to be a very important part of the story in a few minutes. I went to work for Software Bisque, makers of the Paramount and the Sky X software. At first, I was doing a solar system simulator. We had a 3D thing that ran in planetariums, and that didn't do so great. The planetarium business is a tough business, and it turned out imaging was a much better bread and butter. So I spent more time doing imaging and imaging software for Software Bisque, and so I did that for close to 2 decades. Went to star parties representing them, met a lot of people in the business, and kind of really made my connections there. Now, my time at Software Bisque was mostly part-time. I was teaching at a local college, computer graphics programming, and had other things. I've never had just like one job. But I went to work at Lunar G in late 2019. That's a graphics company. It has nothing to do with the moon. The founder liked the moon, so he called the company Lunar Graphics. And I thought, well, that's pretty cool. I was still working kind of quasi for Software Bisque and still kind of doing my own thing. Sort of, I have one career when you can have three, sort of thing. But when I started Lunar G, I did get a little proviso in that standard tech company IP agreement. Because, when you work at a tech company, they're like, if while you're asleep, you have a dream of a flux capacitor, we own it. And I said, okay, so I would like to, I'm actually actively doing work in the amateur and professional astronomy community. So any IP that I come up, IP stands for intellectual property for the non-technical people in the crowd. I said, all of that's mine, and I'm going to keep doing that while I'm working for you, just so you know, I don't sleep that much. And they're like, we think that's really cool. And whatever as long as that brings you joy and happiness. Oh my God, I love working at Lunar G. Such a great company. In February 2022, actually 3 years to the date, 3 years to the day, last Monday, I left Software Bisque completely. I was like, okay, or my part-time was becoming more and more part-time. And I wanted to do some things that weren't a good match for Software Bisque. Because I've got some ideas. I got some ideas that I want to do, and they're not good for Software Bisque. And I'm plus I want to own them, right? I'm getting old. I don't want to be, anyway. So I knew a lot about imaging. I knew a lot about working on tiny computers. I know a lot about the GPUs, the special part of these computers that do graphics processing. And I've always thought that things like live stacking and short exposures were the future of astrophotography. So one of these ideas, that I've been gestating on, is the fact that we don't need to do long exposures. We can do short ones. In fact, I wrote about this in the August 2022 issue of Sky and Telescope with an article called the Next Big Thing. Along the way, I forgot to mention, I also became contributing editor at Sky and Telescope too. So like I said, 3 careers, right? Why just have one? So when I left Software Bisque, I got a lot of phone calls because I put on Facebook, hey, for your information, I don't work at Software Bisque anymore. And it wasn't so much, hey, I hate Software Bisque and I don't work for them, as much as I'm not going to give you free support on your Paramounts and SkyX. unless you're a really good friend. And then, we kind of need to meter that off a little bit, over time, right? But so my friends that I worked with at Starry Night, after the big downfall, when I got laid off, a lot of people got laid off and the company kind of got reorganized, and some people bought that IP, bought that intellectual property from the parent company, and they started simulation curriculum. And so they had Starry Night Pro. They also acquired Sky Safari. They worked with Celestron on the Origin. So they're really cool guys. And like I said, I've known them for 20 years. In fact, every time I run into them at NEAF or something, they go, "Hey, Richard, how's it going at Software Bisque? Are you tired of working there yet?" And I'll be like, "Oh yeah, I'm really happy. It's all good. Thanks." Well, when I left Software Bisque, like I said, I got a lot of phone calls. And I'm like, "No, I'm not looking for another job in the industry. I have some ideas that I want to work on. I've got a really great tech job, and I'm gonna develop some product ideas of my own." And everybody was really cool about it, except for my friend Pedro at Simulation Curriculum, who said, "Well, we kind of want to maybe do something imaging related, and now that you're available, as long as there's no conflict, let's just look. We'll pay you for your time. Let's just meet for a few weeks or a couple of months and talk about some things." And maybe there's some overlap between what we want to make and what you want to make. And I said, "Okay, fine. Okay." And it turns out what they wanted to make was a little box, like an ASI Air sort of thing. And I had worked on that. We had this guy working on a Raspberry Pi before Eagle came out, before ASI Air came out. And it was one of those things. Software Bisque just didn't want to do that, which is one of the reasons I left, so that I could do the sorts of things I wanted to do. And I said, "Look, the box has been done." And I was building on the shoulders of giants at Software Bisque, because I had the Sky, I had all this infrastructure. I said, "We have to start all over from that. We should do something really new and unique." And so there was a group of about 6 of us that were meeting every week, hashing out ideas. And it was a really interesting product development experience. I mean, we were writing stories. Bob, loves astronomy, and his wife thinks it's boring. And how do we get Bob's wife interested in what Bob does? That sort of uh, development thing. And I remembered um, years ago at a Mid-Atlantic Star Party, there was a guy who had a DSLR on the back of his telescope, and he had like a hood thing, and you looked in and you could see the LCD on the back of the DSLR, and he had like a 5-minute exposure of the Andromeda galaxy, or however many minutes it was, and it would refresh every time it took an image. And it's like, this is really cool. It's like looking into an electronic eyepiece, and you see the image there, and that would be neat. One day that would be really cool to have that. Well, I brought that up in the meetings, and Pedro Berganza, he said, we were talking about that too. Like, couldn't you put like an eyepiece and a computer and a camera all together, back in November? So we kind of had, both me and Pedro had kind of this idea independently. And so we both brought it up at the meeting, and I made this little diagram for the muggles, which is the managers, who were there. And I said, "Look, this was an attic camera at the time." And I said, "Look, this is all it is." I said, "You got a camera down here, you got a little computer in here. They're making little stick computers that are the size of a jump drive, right? And we put like a little display right there. And the camera takes a picture, the computer can live stack right inside the camera." Live stacking, by the way, a geeky word. Basically, we're taking lots of short exposures and we're aligning and combining them, and we're doing it on the fly. So, like most deep sky exposures, imagers, they'll take lots of, dozens of images, and then they'll use PixInsight or Deep Sky Stacker or something to stack it after the fact. And there were a couple of products on the market that did what we call live stacking. I even implemented live stacking for the Sky X Professional. It does live stacking. And I said, "Look, I've done live stacking before, and I've done auto stretching algorithms before. So I basically know how to do this. We could put this together." And so it's like, "All right, let's extend your contract." And this was kind of along the lines, I was thinking of making a little box that just did live stacking. So this is like, all right, this is a natural extension of one of the 3 things I wanted to build when I left Software Bisque. So, initially they were like, hey, maybe we can build this for like around $300. Um, we found some websites. There's some guys with Raspberry Pis, and they've got this $12 camera, and they're putting it on a Dobsonian, and they're getting a picture of a galaxy. And I'm like, yeah, that's great, but I don't think that's going to work. Um, the camera that works okay. If you take a long enough exposure, you can get something that looks kind of representative, but you really need a camera that's a lot more sensitive and is geared towards astrophotography. But one of my favorite quotes that I use all the time in a meeting is, "A single test is worth 1,000 expert opinions." And so we tried it. We got a Raspberry, the most expensive Raspberry Pi built-in camera you could buy, like $12.95, right? $12.95. And we 3D printed this little thing here. We put a Raspberry Pi on it, and I put that on the telescope in the backyard, and we did some experiments. And then I took a Player One Neptune, and I stuck that in. I did exactly the same exposures. And I said, here's the Raspberry Pi, here's the Neptune. And they said, yeah, we're not going to be able to do this for $300. Do we want to do this? I mean, do we want to make a premium product that's expensive? Because we don't. Lots of people complain about the cost of the C Star, right? What if this is $1,000? Oh, nobody's going to want to pay that. We got through that period, and they decided let's keep going with it. But simulation curriculum, they make Sky Safari, they make Starry Night Pro, they make software. They do have something called SkyFi, which is a little box that turns your telescope into a Wi-Fi hotspot. But they don't make hardware. We don't want to make cameras. I mean, this is great, but this is the science fair project, right? This is not a product. So we needed to talk to a manufacturer who, we go, hey, this is a great idea. We want to get on board. By this time, we had a patent actually in the work. Pedro and my name's on the patent for it. But we need a manufacturing partner, and I'll spare you the list of who we did not want to work with and who we thought might work okay. But some guy named Seth knew some guy named Sachin, and it turned out some people knew. In business, it's always who you know, right? It's your networking, who you know, who knows, and who you like, and you work with who you like, not because you like them, but because you trust people you like. And so, Pegasus Astro. At NEAF 2023, we approached them as a manufacturing partner, and they were very excited about the idea. There was already, there weren't a lot of, anyway, they were very excited about the idea, and they were like, hey, this sounds great. We always wanted to do a camera, but making a camera is really complicated. But, if you've got a relationship with an OEM, and by this time I had sort of picked an OEM that I thought was the best pick for the product. And so they came on, early 2023 as the manufacturing partner. And, just to sort of fast forward a little bit at this point, I just want to mention that, they weren't this wasn't like our great idea and Pegasus is making it for us. Once they joined the project, they really contributed very substantially to the design of the eyepiece. For a lot of innovations in the electronics and how it's going to work. And they had some experience imaging too, so they had some input on the product. So really, at this point, it really became a full collaboration between Pegasus Astro and simulation curriculum, and then me kind of dangling off. They did ask if I wanted my name on the side of the eyepiece, like Starstone, and I was like, no, I'd rather not do that. At this point, I sort of knew what sensors I wanted to use. We wanted to use and what OEM we wanted to use. And just, it takes a long time to develop a product. One of the interesting things I did was at the 2023 Grand Canyon Star Party, I took 10 cameras to the Star Party. And, this is a lot of work, right? One night, I've got a telescope, same optic, take some test short exposures at different gains with this camera. Then take another set of test exposures with different gains with this camera. And then, to do that multiple times, and then go back and go through all that data and, quantitatively, objectively figure out which one is the best. You don't get on cloudy nights and go, hey, who makes the best astronomy camera and run with that. In fact, it's very interesting, kind of an interesting there are a lot of interesting twists and turns. It's like in a movie. It's like, oh, things are going to be great, and then something happens. One of the setbacks was, Pegasus Astro. They're like, why are we going with? I'll just tell you, it's player one with the OEM. I've worked with when I was at Software Bisque. I've worked with pretty much every manufacturer on the market. I know people at the manufacturers. I've worked with them on their software development kits. I know their engineering teams, and I know which ones are awful and I know which ones are good. And the most impressive team, hardware and software, that I know about was Player One. Yeah, FLI back in the day would have been a close contender, but they had some problems and they're also very, very expensive. But okay, we're going to go with Player One. Well, Pegasus, being responsible. Well, who's this guy in Florida who says we should use Player One? We got some quotes. If we want to make 500, if we want to make 1,000, how many per unit? And like, we've got this other vendor, I won't give you the name, and they can do it for half as much money as Player One. And I said, I've worked with them and they're awful. And they're like, well, how bad could it be? Lots of people use their cameras and they get good pictures. And I'm like, yeah, they're doing great pictures with long exposures. The noise, there's more to a camera than this chip. The electronics around the chip also contribute noise to the camera. In fact, we learned this the hard way because some of the electronics in SmartEye were adding noise to it. One of the manager guys, he wanted the eyepiece to talk like the ZWO stuff does. He wanted a speaker in it. Well, that amplifier was so much noise that it was affecting both the camera and the little crown that you use to work the menu and things. But it's funny, the littlest things you add have the most sometimes really bad consequences. Where was I? So we had to get the camera module from this other camera company, and of course I had to do a very scientific, same images, same target, same scope, same night look. And you're like, wow, that's awful. I mean, that's really awful. I don't understand. I'm like, well, because we're doing really short exposures. The noise is more important for short exposures than it is for longer exposures. And so we contacted them. They said, yeah, it was an engineering sample. Let's send you a commercial pooled camera. It'll be much better. It was a little better, but it was still awful. And it's like, okay, we've wasted enough time on this. We're just going to go with Player One. So Player One is the OEM. They're actually making the module. And this is one of the important things, that Pegasus Astro, Player One did not have a camera that cooled with a USB-C only power connection. And so this is kind of an innovation. We may even see, Player One cameras down the road that are powered by USB-C. Pretty cool. So, all right, we've picked a camera module. It's an IMX 533 commercial grade sensor on an OEM board. It's time to start putting all of this stuff together. This was second prototype. It was just basically a proof. How can we? It had a camera in it, and it had a display in it. So we found, a really high resolution display. I had been playing with this really crappy $12 round circular display I found on Amazon. Oh no, we got to have a nice 4K display, OLED, and all this sort of thing, and a diopter so you can focus on it. And so the second prototype here, it basically had a USB for the camera, 12-volt power, and then an HDMI port that would feed the display. And so what I did was on my laptop or on a Raspberry Pi, I would plug the camera into my laptop or computer, and then I'd plug the USB into this, and I could sit outside at the telescope, see the image, and see how it's stacked. Because the image looks very different on the display in SmartEye than it does on the screen. And so this is the prototype we had, and we were to the point to where, Simulation Curriculum and Pegasus both had invested a lot of money. I've got some sweat equity, so to speak, but I've not put out money, so to speak. In fact, I've figured out a way to get paid a little. Never mind, we shouldn't go into all those details. Anyway, here it is. Here's a working prototype, even though the computer is not inside. I've demonstrated that the computer, on the side of the box can do it all. And integrating all that together is going to be a lot of engineering work, right? And it worked. We had the test data. You could plug it into a small Raspberry Pi, and it would display it on the output and all that. And that was good. Now comes all right. we've put a lot into this. We put a lot of time into this. Is it go, no go? So the major decision to whether we're going to finance this all the way, he flies to Florida, and I meet him, at a nearby hotel, and so I brought this, and I said, okay, I said, so the live stacking is great. C-Star does live stacking. In fact, here's a C-Star image on my cell phone of the Horsehead Nebula, right, and here it is on the phone, and this thing, the C-Star's over here, and it's imaging the Horsehead Nebula, and that's an experience a lot of people like. You can see it, but imagine you walk up to the telescope and you look in the eyepiece, and the display on this is much brighter and much more vivid than your phone or your eyepiece. And the money guy was like, yeah, we're going to make a fortune with this. This is going to work. This is better than I expected. And, he went back and talked to the other, money guy. I hate to call them the money guys. They're really nice people. I know them by name, but you don't need to know them by name. Really nice people, know a lot about astronomy and the industry. And they were like, yeah, this is a viable product. We need to bring this to market. I posted this on Facebook not long ago, kind of how it started, how it's going. The third prototype is what you see here on the right. And this was a full sort of working prototype. It had a computer in it. We used a compute module inside of it. It has the IMX sensor. It has the display, and it works. And so we brought this to NEAF in 2024, only about a year ago now, a little less than a year ago, and we showed it off. You can't show this, outside. I mean, you're in an auditorium, right? So it's some pre-made images, and said, come and see what the images look like in the eyepiece, and see if Plus, this is really important for us too, because a very valid critique is there's lots of smart telescopes on the market. Do we need a smart eyepiece? Does that eyepiece experience really go, wow, that's what we want? And so we got to show this to a couple hundred people, and most of them were like, wow, this is really great. This is going to be really great. When can I buy it? All that sort of thing. So that was very, also very validating for us, and very energizing, moving it forward. So we're working on it. We continuing to make hardware tweaks and so forth. In August of 2024, again, not that long ago, we showed it off at a public event, Starfest, which is a big star party in Canada, which, by the way, is a huge star party. Very well organized. I just have to plug them. Lots of vendors, lots of speakers, lots of people. I mean, like 800 people or so are at the star party. It was really great. And we showed it off live there. Like, walk up, see it, and we would change targets, and you could see the image develop in front of you. And we got incredible feedback from everybody, and we knew that we gotta deliver on this now. This was really the first time anybody other than me and the guy in the yellow shirt had ever seen the SmartEye actually working, like under a dark sky. Like, okay, let's go to the Trifid Nebula and see what it looks like. So lots of people got it, including Pedro, kind of the co-inventor of the idea. He'd never gotten a chance to even look through one either up until that time. This brings us to sort of the present, the fourth generation prototype, which is the one on the left here. This is there's still a couple more tweaks before production. This is like the last real prototype. This is fully functional, USB powered, cooled camera. It's about the size of a 31 millimeter Nagler, so like the holy hand grenade. It's not bigger than a real eyepiece. There are eyepieces that are this big. It is a little bit lighter than a 31 millimeter Nagler. So computers and aluminum is lighter than glass. Who knew? It's a little bigger than the one on the right because of the tech, the thermoelectric cooling that had to be in there. We also wanted to work as a full-fledged astro camera. So you put it on a real telescope and connect to it with Alpaca. So it's sort of cross-platform. It's kind of an ASCOM sort of thing. And so you can use it as a real IMX533 sensor, and it's cool. And you can do long exposure photography with it, as well as using it as a live stacking doohickey. The last couple, just to give you insider stuff, that's what you're here for, right? This has the audio hardware, but it's disabled. So the final one's not going to have the audio hardware in it at all. And we have a desiccant plug that's going to go in the final one so that to keep the chamber dry, and it's replaceable, which is what a lot of vendors are doing these days instead of the old argon cooled stuff. Argon purged chambers is great and all, but they always leak, and you always got it, and they're a pain in the butt. And the desiccant seems to work pretty well. So lots of people are going that way. So that's where we are. We showed this off at the Winter Star Party. Let me show you. I think this is a video. Yeah, this is. I'm going to talk over the sound. I forgot this one had sound. You can still hear me, I hope. Nod if you can hear me, Frank. Okay, good. So I made a video showing, it's a little bit accelerated. This is about a couple of minutes. The very first image is black and white and faint, but it's like you would see in a really large telescope. So this is, I think I made this with a 6-inch refractor, but it looks like the Trifid looks in a big daub right away. First image, it looks like you're looking through a big daub, and then every 10 seconds, the image gets brighter and brighter. We didn't want to just show a noisy image that gradually gets clean. It's funny when we were showing this off in Canada, it was like, it's almost like it's too fast. Right away, you get this image. So as you get more and more data, what we call the signal to noise ratio, the image gets cleaner. As the image gets cleaner, we brighten the image and fill it out, and then we start to fade in the color until you get a full color image. It only takes a couple of minutes to get there. Let's go to the Winter Star Party. So this was just last week. Was it last week? Yes, it was just last week. We were at the Winter Star Party. We had 3 of these at the Star Party. Pegasus Astro had one on a little Astro Takahashi 85, and then a Spree 120. And then my friend has an 8-inch tech refractor, and it's f9. And I was like, it's a little slow. I don't know if it's going to work. It worked fantastic. And in fact, I think more people came to look at it through the big refractor than they did the smaller scopes. Here's another video. This was taken by the Pegasus Astro guys, just on their phone, holding the phone up to the eyepiece. And you can see the Whirlpool Galaxy there. It develops quite nicely, and that's my contribution, is sort of the auto processing and auto stretching on it that pulls it up. Let's see, here's another image. This is from Starfest in Canada. You can also, these are saved images because you can save the image on the SD card. You can also connect with your phone and see the image on your phone if you want to do it that way. Here's M81 and M82. Here's some images with, taken on the phone, connected to see what they look like. They're dimmer on the phone. The eyepiece is a much brighter, more vivid experience. I think that's really, in my opinion, kind of the selling point. Here's some of my very poor cell phone photography, holding it up to the eyepiece. The diopter, if you're not really close to it, you get a lot of coma. The closer you get, the stars all turn around as you get closer. But these are just a couple of minutes on these targets. With this sensor that we spent a lot of time figuring out what's the right gain to use. You can also take dark frames with it, and it'll apply the dark frames. And then there's some Mojo secret sauce I put in there for getting rid of the remaining hot pixels. But we got M51, Thor's helmet. And again, this is on a f9 refractor. I was really quite happy with that. And then Centaurus A, one of my favorite objects down there from the Star Party. And so there we are. That's the product. It integrates in real time. It is cooled. It goes down to 30, 35 degrees below ambient. It does have Wi-Fi, so you can connect with your cell phone. If you have Sky Safari, you can work it with Sky Safari. There's actually a button on the device, kind of like working a smartwatch. You can press the button and scroll up and down through the menus, and you can modify the exposure time and do different kinds of settings and things. The image is shareable with any web browser. It can be used standalone. It takes an SD card for raw data access. It's a FAT file system, so any computer will read it. So if you got an SD card, you can read it. We'll probably have a way to transfer files over Wi-Fi too if you don't have an SD card. And it uses USB-C as power input. Also, I want to, just point out kind of what's happens at the Winter Star Party too. Is a lot of my friends are like, "This is Richard's product." It's not my product. There's about 10 people working on this. All right, besides me. The core four or so. This is one of our weekly engineering meetings. Pedro's in the bottom corner. Evans from Pegasus Astro in the bottom right-hand corner, and then me, and then Rudolph Pinu. I worked with him at Software Bisque on Fusion, and he and I have been friends for years. And he'd actually already worked with Pegasus Astro. And early on in the project, I said, "I am the applications guy. I can do all the imaging stuff. We need an OS guy. I can do that, but it's going to take me a long time, and I'm not going to quit my J job, quite yet." I know a guy, Rudolph, and it's like, "Oh, we know Rudolph. He's easy to work with." So probably these four are the core, but there's like 6 other people that are working on this really regularly. 2 of them are Sky Safari people who work regularly on Sky Safari. They're doing the very non-inconsiderable amount of work being done to make Sky Safari and SmartEye talk to each other, so you can control it through Sky Safari. You'll be able to this is my picture, and put it on the sky chart where the object is and share it, with the world. We got a web guy who's doing the web interface stuff, and anyway, there's a lot of people that are working on this, besides me. That's it. Questions?
Oh, I have
I should
many.
turn up my sound so I can hear. All right.
Cool. Yeah, we have a few. So in the chat, Dave LeGros asks, you talked about the raw image transfer there. Is that in FITS format?
Yes. Yes, it saves FITS files for you if you want them as FITS.
Cool. And I see Brock Rosser, you've got a hand up, so go ahead and unmute yourself.
Hey, very exciting stuff there. Just a few quick questions. Your examples were showing, I think, the refractors. I've got an 8-inch Celestron reflector. Will this work with that, or?
Yeah, probably. So it's very early, and we're telling people F7 or better. However, I tested on my F13 Mac Cassegrain, and on brighter objects, it works fine. I wouldn't try to shoot, the Bat Nebula, in narrowband H02. The focal ratio is really the key thing, and I was a little worried about the F9 refractor, but it did great. So I think unofficially F10 is going to be fine. I'm assuming your Schmidt Cassegrain is F10, right?
Believe so. I can check that out.
Yeah.
And then secondly,
Yeah,
you're
most of them
using
are.
you're using Sky Safari to power this, but I'm using the Celestron Sky Portal Wi-Fi. So how is that going to conflict for me to be able to navigate? Are you going to be able to have your product be able to use 'cause I've got to have something to power my telescope to find things.
Yeah. So the Sky Safari integration is optional. The eyepiece will work by itself. You do not have to have Sky Safari or a smartphone at all. You can just put it on your telescope and turn it on. The USB-C is the power, and use whatever you want to use to get on target, just like you would use a regular eyepiece. Get on target and then put this in. It has a live view mode where you can focus. The live view mode is 1/10 of a second, which is fast enough, long enough to accumulate enough to see lots of stars, but fast enough to get real-time feedback as you're moving the focuser and getting the stars to be, nice and small. We are working on, and this is probably we're gonna have this ready in April, like in late April. And vendors are taking pre-orders now. In fact, all of the first production run is already pre-sold to vendors. But we want to do a lot of fancy things with the Wi-Fi. If Sky Safari is controlling your telescope and can talk to the eyepiece, we can do plate solving and help it get on target so that you can get on target very easily. So that's still kind of to be determined how we're going to make all that work with a really diverse system. Now, you're using Sky Portal. Guess who wrote Sky Portal? Sky Safari. So that I'm confident that that will integrate nicely in time. But I want to emphasize that you do not have to use Sky Safari to use the eyepiece. It's 100% perfectly functional without any connection from a smartphone at all. There's a little menu in there, and you look and you can move the menu up and down and tell it what you want to do and all that sort of thing.
Thank you.
Awesome. Another Richard asks, can you talk about the price point?
$15.99. It's not cheap to make. It's not like jewelry where you mark it up 100% or something like that. Yeah, they're not cheap to make.
I would have guessed more, actually.
Yeah.
Luke asks, does it have a battery or does it need to be plugged into USB-C at all times?
It needs to be plugged in at all times. We thought about doing a battery, but because it's cooled, it requires a lot of juice. Big batteries are hard to we're shipping complications, all sorts of things. So like your own USB power adapter or a power tank, should be sufficient to run it.
Cool. Bill Castro says, hey, what's this going to do to your night vision?
Hey, so it's going to ruin it. So here's the thing. A couple of things to mitigate. One is the display can be dimmed down a bit, so it's not so bright. Second is, for the most use cases, we see this. It's going to be very popular for outreach, and in your front yard, in your backyard, or in your driveway. And let's be honest, at the parking lot at Starbucks and in your driveway, you're not going to have a lot of dark adaptation. So what did we do at the Star Party? Very simple solution. Guess what? You have two eyeballs. And so you look in the SmartEye with one eye, and you look in the other eyepieces with your other eye. And that's what we did, at the event, because we were under, reasonably dark skies, and people did want to kind of have some semblance of dark adaptation. Yeah.
Cool. Yeah, I mean, I guess conceptually, it's kind of like looking through an EV scope, right? So how would you compare it to that product?
It's a very different experience. The EV product is live. It is substantially brighter, and you get the results immediately with it. The night vision stuff, you're talking about night vision, right?
Yeah.
Yeah. The night vision stuff is it's a different type of experience. It's like, chocolate and vanilla ice cream. They're both ice cream, but or maybe ice cream and pie. Some people like ice cream more than they like pie. It's a different experience. It's also, even at $1,600, it's a lot cheaper than night vision is, for sure.
Sure.
One thing I kind of want to do, I don't have time to do it for first release. I'll be working on this for a long, long time. They'll have releases regularly, but I want to have like a night vision mode that kind of fakes the night vision appearance, even like with some random sparkles and things like that. Like you're looking through a night vision, like make it green and very dim. That's another thing that can help with night vision too, is a very dim green display. The human eye can adapt to that very easily. You're actually your eye's more sensitive to green than it is to red, and it's very, very dim. The green doesn't ruin your night vision, but your eye can actually discern the contrast. So a little bit of a segue there, but yeah, different from night vision.
Yeah. There was also that Unistellar telescope too, right? They had like kind of that eyepiece that was actually a display. How would you compare it to that one?
I think our stacking is as good or better than theirs. You can put this eyepiece in any telescope. So you can put it in a real telescope. And I hate to be, not that I want to downgrade it at all. C-Star is great and everything, but it's a 200 millimeter camera lens. You can pop this in your 8-inch SCT. You can pop this in your 6-inch refractor. You can pop this in your 80 millimeter refractor. Uh, and you can carry it around and you can use it with all your telescopes. And you can take it to an event and stick it in your friend's Dobsonian.
Mhm.
I should mention you do need a tracking telescope, but Altaz is okay. Um, it, 10 seconds actually turns out is long enough for Altaz. And people go, well, what about field rotation? Yeah, what about image? What about image stacking and alignment? It's we
Mhm.
derotate images all the time. It's not a big deal. Um,
Right.
so yeah, there was one of those at the Winter Star Party, and they're nice. But like I said, you put this in any telescope. You put this in the telescope you have, telescope you already know and like, and like my wife comes out and she'll look at a galaxy and it's like, photons traveled millions of years and that intergalactic energy is entering my body. And she's like,
Yes.
the bugs are getting me. Are we done yet? It looks like snot on your eyepiece. I don't see anything. Well, with
Right.
this, your family members and the muggles, right, at Outreach, they can look in there and go, oh, that looks like a galaxy. That's really cool. That's amazing. It's a very different response to it. And like I said, it'll work with the telescope you already have. So yeah, I think there's room for those products also. It's a different, it's a different kind of thing. There's no one automobile that's perfect for everybody either, right? Some people need trucks, some people need cars, some people want a convertible.
Yeah, that's awesome. I really love what you did there with like going from monochrome and then blending in the color when it wasn't like all color noise too. That's
Hmm.
cool. I just want to say.
Thank
Um,
you. Thank you. My
couple
idea.
more, of course. Jeffrey Martin's asking, what about planetary? Does this work on Jupiter and Saturn with the right scope? And how does it work with heavily light polluted skies like Bortle 7 to 9?
So it works pretty good. And let me do the last one first. Works pretty good with light polluted skies. Um, It works. We've tried it with several light pollution filters and the tri-band nebula filters. You need to increase the exposure time a little bit. If it's a slow scope, you don't want to put a nebula filter on an F10 scope and try to do 10-second exposures. But if you can up the exposure to like 20 seconds on an equatorially mounted scope, it works great with light pollution filters. Even without light pollution, it does pretty good. The thing about light pollution is it adds a constant light level to everything. And the algorithm that I came up with, it's doing the same thing you would do in Photoshop or PixInsight. It goes, here's the histogram, and it just says move the black point and apply some math, and then move the black point again, and so forth. And it does a pretty good job of giving you a good image with a dark background and the features of the object. I live stacked long before this project, back when I was still at Software Bisque. I was live stacking the Andromeda Galaxy from the Starbucks parking lot. And that was sort of we assume we can't do a lot of things, but it's like the data is there. You have to, the thing about light pollution is a lot of people are getting almost as good results from light polluted sites as people do from dark sky sites. You just have to expose a lot longer. So instead of 3 hours at a dark sky site, you need to expose for 3 weeks, under light polluted. But the data is there, and in a couple of minutes, you can get something that looks like a galaxy or looks like an object. Now the planets, I keep having to wave off, the marketing business management people because it's kind of like it's like we want to say you can use it for planets too. I'm like, well, okay, but I don't think we should warrant for planets. Maybe a software update later we can do planets. I do have auto exposure. It works great on the moon. So it goes, oh, I'm oversaturated in live view mode, and it'll automatically turn on the auto exposure mode, and you can see the moon. I've gotten it to work on Jupiter and on Jupiter. The key phrases there, I've gotten it to work. I really don't. I don't want to tell people that it's great for planets until I've gotten the software to where it's great for planets. And that's not the focus for the first release. So
Right.
eventually, yes. Right now, when it ships, if you're really industrious and patient, you could probably make it work on the planets in live view mode only. It's not gonna stack the planets. Um, we could do that eventually. But as I keep saying, I can't mow the grass and do the dishes at the same time. So it's not going to be in the first release.
Right. And that's a great segue to Dave LeGros' question. Will software be upgradable on this thing going forward?
Oh yeah. Oh yeah. Yeah. We were having a bit of a meltdown recently, and so because we we just got to do this, and the longer you work on it, and the more you do, the more the feature list keeps getting long. It's like, all right, no, we really haven't taken the time to go, what's the minimally viable product, and we came up with that. And the minimally viable product is a list this big, and the list of things we want to do is this big. I would anticipate monthly updates for a year or two or three. And we decided too that that's a good thing. You know, ASI Air was awful when it first came out, right? It wasn't awful, but I mean, it didn't do near what it does now. And products released, there's regular updates, not just bug fixes, but works great on planets, with this update, or we got a new focus assist feature, or we got a new, little things every month we'll have or so, we're gonna have new features. And you'll be able to update it with, like Sky Safari, connect to it. There's an update, it'll automatically update it. I think there's going to be a way to put the update, download the update file and put it on the SD card. And when you stick it in, it goes, oh, I see an update file on the SD card, and it'll do the update. But yeah, that's a robust update mechanism is like the most important feature. There's no such thing as bug-free software. Like the week after we ship them, we're going to have an important fix that we're going to want people to have, much less we want the product to be vibrant and alive. I mean, not only do we have a whole list of software features, but there's future hardware versions of this that we're thinking about as well. So yeah, it's going to be a very vibrant and growing product, moving forward after we release it. Like I said, the whole first production run is already sold out to distributors. And every time we show it off, there's a couple of people who are like, yeah, this just isn't for me. But overwhelmingly, it's like, holy crap. We were going to call it, we thought we might need to rename it the OS eyepiece, because people would look in and they would say OS. And so it's going to be growing anyway.
Awesome.
Yeah. So yes,
I'll-
there'll be updates.
Cool. Brock's other question here is a good one to wrap up on. Is there a way to buy directly from you so you can get a bigger percentage?
No, no, I am not making it. You would not be surprised how many people like, hey Richard, can you get me an early copy? Hey Richard, I want a beta test for it. Hey Richard, can you? No, Richard can't. Richard, Pegasus Astro is making them, not me. They're not cheap, so it's not like when I was working on software and I could slip you a copy.
Mhm.
And they're not cheap to make either. So in fact, Pegasus, Lord have mercy, they're tight sometimes with, why didn't you make more prototypes so that we could have more people, looking at it? Early on, we never mind. I don't want to say too much. Anyway, yeah, no, you can't buy directly from me. I'm not a distributor. I'm not a reseller. I'm getting compensated. It's all good. Thank you. But yeah, buy from one of the dealers. That's fine. Yeah.
Awesome. Wow. I wish you amazing success with this. I can't wait to see it myself. But this is awesome. This is like change the world stuff. So congratulations, man. That's great.
Thanks.
Yeah.
We're very excited about it too.
Awesome. Thanks so much for giving us the story there. I have more questions, but I'll wait till I see you in person because
Okay.
we're running out of time here.
Okay.
Thanks so much,
All right.
Richard.
You're
And
welcome.
stick around though. We have one of your astrophotos coming up here. So let me switch
I'm
gears.
sticking around. Yeah,
Good,
I'm
good.
sticking around.
So let
Can't
me
find how to turn off my screen share. Maybe just
I'm
take
trying
it
to
away from
figure
me.
that out too. Let me see. Stop sharing. There we go. I have
There we go.
wrested control from you. And
Right.
let me regain it. Yes, so thanks everyone for hanging out with us. I know we're running a little bit late tonight, but we're going to wrap things up with our astrophotography and sketching showcase. And guess who's first? It's Richard Wright. Hey, what do we got here?
Hi, Nebula. The very first Messier. Taking at the Winter Star Party. So I was really busy at the Winter Star Party, and I brought too much stuff and didn't have time to do anything. And the dew was apocalyptic. I know you like that name, Apocalyptic Dew. But I have a fairly new to me C14, which is a really big scope with a big plate of glass pointing up in the air. And I did some planetary imaging with it, which came out okay. But a friend of mine in Canada is like, Richard, you need to do some deep sky imaging with this telescope. And I'm like, well, I'll try it. And so I shot the Crab Nebula. Um, I only got a little over, I don't remember, I think slightly less than 2 hours before the dew just got to be too much. One night when I wasn't demoing SmartEye, and came back and processed this Crab Nebula. And I'm like, well, by golly, the seeing in the Keys is really, really good. And so I think the image scale on this was zero point 0.6 arc seconds per
Hmm.
pixel, which is pretty crazy, crazy small. But it came out really nice. I'm like, I've shot the crab several times and I've really never liked it. And this one I like, I like this. I like this. It's a little, the background's a little modeled on the, anyway. Yeah, so that's it. Crab Nebula, 14-inch C14 f11 with a Player One Zeus one-shot color camera. It was binned 3x3,
Hmm.
and all the normal stuff, Pixel Sight, Photoshop, that sort of thing to process it. Turned out
Yeah,
mighty. 1 minute exposures, not even very long exposures, just like 117 1 minute exposures. So
cool.
unguided.
I see you got one of those new mighties with the absolute encoders too. How's that working out?
I did. It's really nice. There's no periodic error. So if you've got a good polar alignment, you can go unguided for extended periods of time. I really wanted to press this setup to its limits. As you can tell, I spend a lot of time working. So this system, I really was like, I'm going to go down there and I'm going to have all week to work on this, and I'm going to really see how far I can push it. And of course, I didn't have any time to do any of that. Next week or next new moon, I'll be down in my spot in Okeechobee. I'm taking it down there, and but from what I can tell, no periodic error is pretty nice. The mount modeling on the Paramount is great. I did not want to spend the time figuring out how long I could go. Once I could see 1 minute exposures, I got lots of data with 1 minute, so I just stopped and I shot 1 minute. Like I said, the dew was, I did not have a hair dryer with me,
Hmm.
and I could not keep the dew off that 14-inch plate glass. Not plate glass, but you know what I mean.
Yeah.
So it was like, I have a very short window. Do I want to see how long I can go, or do I want to get some data? And it's like, I want to get some data. So I just 1 minute, I did 1 minute exposures, and it's like, it looks 1 minute, I've got all the data I need. So I just went with that. Got 2 hours.
Yep. Yep.
Mighty's great.
Awesome. Yeah, that is awesome. I too have tried imaging M1 several times, and I never get much more than a smudge, because my focal length is too short, my seeing sucks. So this is
Hmm.
a really great result. Awesome. Thanks so much. Up next, William Castro. I know you're here. If you want to take yourself off of mute, we got some moon action here.
Yeah, this was at Geneva, Geneva night the other week. And it didn't look like it was going to be a good night, so I didn't bring my best scope, but the turned out to be really good. I should have brought a better one. I wouldn't have gotten any of that little discoloration on the limb there. But the moon was a small crescent, and we always tend to ignore that. So with my diagonal and all that, north is south, or towards the bottom, I mean. And but I got a good view of Mare Crisium and the other Mare above it. Since we're recording, I'm not going to try to pronounce that. I'll butcher it. I don't want to go there. But that was a pretty neat example of how these Mare and the impact basins form. It was explained in that Modern Moon by Charles Wood. You can read how it's there. It responds like a pebble dropping into some water there, and then the waves kind of freeze in place. And I could really see them in that one picture. Go to the next slide there. I kind of circled them around, and I've got them numbers by the circles. And the main circle is number 3. That's the Crisium ring. But inside that wrinkle ridge ring really stood out. It looked a lot better through the eyepiece, of course. These are taken with the iPhone, just handheld to the eyepiece. But then that outer ring too kind of shows up on the left side. You can, if you look for space in between the mountain and then another batch of mountains, there's some flat parts. There's a lot of other cratering going on. But if you look for that, you can really notice it at the right sun angle. And then the next slide is that the mare above, which I refuse to pronounce while I'm being recorded, but that's an example of two craters that are next to that mare, and one is older and one is younger. And Linus is the older one. It's mare filled and battered pre-Nectarian craters. Central Peak is covered with the lava flow shortly after the formation of that mare. And then the younger one is Copernican to the other age crater. And you can still see it has a central peak. So the main thing is the mare was already formed and didn't flood into that area, so the central peak's still visible. So that's another way of telling which is a younger or older crater.
Very cool. Yep. And finally, an image.
And then this one, I took it home with a little better scope, still an iPhone at the eyepiece, similar magnification, and but all the crater rays really popped out on that one. Those are all younger craters that show all that rays. That just looked kind of neat to me. And I tweaked it a little bit on my iPad, but not much.
Very nice. Yeah, and if anyone's watching this on YouTube and you want to learn more about lunar observing resources, make sure you watch our January meeting as well. We had a whole mini program on that too. So thank you so much. Up next, we got Wes Clem. Wes, I think you're still here. There you are.
Hey.
Hey. What have we here?
That is the Eta Carina Nebula. Got this at the Winter Star Party. And this guy, if I recall, it was only about 5.5 or 6 degrees above the horizon. Like it was just so low. My scope looked like it was pointing at the ground. I thought for sure, like, I'm not getting anything from this. And then about 1 hour each night, I think this is a total of about 3 hours, SHO. And it just came out just so much better than I could have ever imagined. I really was surprised how much data was there. I mean, it's a testament to how bright this thing is that 5 degrees up, this much came through in just 3 hours. So if anybody's ever seen the James Webb Telescope image, one of those very first ones, that cosmic cliffs, that's down there, like the lower left, that little blue circular area down on the lower left. That's where that is. Yeah, down there.
That's amazing. That's like a bucket list object for me and for most of us, I think. That's incredible. Speaking of bucket list objects.
Yeah, the Omega Centauri, big globular cluster. You could basically see this naked eye. I think this I think it got up to about 17 degrees, something like that, 19 degrees. It was also fairly low. And this was only an hour of RGB across a couple of nights, only getting about 15 or 20 minutes a night on this between like other things I was trying to do. So it's just huge. It's such a big globular cluster. When you compare, if you've imaged other ones before and then like put them side by side, that's when you can really see the scale of how big this guy is. The height of this frame is about a full moon. So that gives you an idea of how big this thing is.
Yep. Nice processing too, by the way. Like a challenge with globs is, not having the core blown out, and you still have some really good detail there. So
thank you.
Nicely done. Good color too. And up next.
This is the central area of the Question Mark Nebula. I did this one at home, so this was over the course of like December and January, and this one is close to 30 hours in total of SHO. So I really wanted to go deep on this. I really wanted to get a lot of detail out of all of those little pillars, and I love how this one turned out. It's one of my favorite ones I've ever done.
Awesome. Tying back to our main presenter, I think there might be some star forming regions in there. if I'm not mistaken.
Absolutely. I think the cluster that forms this is in the upper left up there,
Mhm.
where all of the pillars are sort of pointing toward it. So
Yep.
that was another cool thing is seeing how like, oh, that's where it's all coming from. That cluster there is causing all this craziness.
Yeah, that's right. We kind of like see those pillars as kind of like growing from the bottom up because that's where we're used to on Earth, but really they're being blown back from the
Mhm.
wind of that cluster. So
Exactly.
very cool. And
And
another good
lastly,
segue.
for speaking of Smart Eye, I just wanted to highlight like this was an iPhone smash on the Smart Eye of I think this was maybe 10 or 20 minutes. I'm not really sure how long it had been going, but it was on that big 8-inch refractor. And I just wanted to show off, like, this is what a user is going to see when, like, when an outreach person, like, the muggle, as Richard said, walks up and they're going to see this. They're going to be like, OS, like, there it is. There's M51. And
Yep.
like it was really cool to see those things just pop into existence right there. You're sitting around chatting, go back and check. Oh, and it looks better. So it was fun to play with. And I just wanted to show this is my iPhone to the eyepiece. This isn't from the app or anything. So
Hmm.
it just looked really cool.
Yeah, that's awesome. Gosh. Awesome, awesome stuff. I've got Winter Star Party envy now, so nice job.
Join us next year.
I just might. Robert Santillana, I think you're here. Doo-doo.
Yeah, I'm still here.
Okay, cool. Yeah, what do we got?
Well, this was something I took off my Sea Star when we were at Town Park this past weekend doing the Avalon outreach. Um, the I understand why everybody really would be excited by Richard's project and the new eyepiece because this started and people were just really enjoying the building
Mhm.
of this image. They kept coming back and checking on it to see what the progress was. And it was really just like an oh my God kind of thing. This is like 38 minutes of exposure. And of course, it's the Orion Nebula.
Yeah, it's actually really nice. And I think I see a hint of the Running Man Nebula at the top there too. So that's kind of awesome. Avalon Park, that was a big one. Like, what was that event like for you?
Oh, that was just wonderful. Um, Lots of people always like going to do outreach things. I get limited because of Lori, but she really enjoys being there as well and interacting with all the folks. It's a great
Yeah,
event.
thanks for participating in that. That was a big one. Lots of outreach opportunities. Again, if you want to get involved, fire off a note to outreach@cfas.org. Cal Beard, the mighty comet hunter.
Howdy.
Hey, what do we got?
So I've just been chasing comets with my Sea Star, and I've been able to locate 14th magnitude comets. And I was pretty
Nice.
impressed that my Sea Star was able to do that. This is from the Chiefland Star Party.
Very cool.
This comparison of my live image with the Carte de Ciel.
Got it. Got it. Yeah, that's it. Yeah, definitely clear as day.
Sometimes comets are not that exciting, but there it is.
Just finding them, yeah, that's kind of awesome. Like I
Yeah.
didn't actually know the Sea Star could track on comets. Does it have like a special mode for that or anything?
No, actually, it makes a smear if the
Okay.
comet is going. I have to restack with serial or something
All right. You can get
to get it
the raw
straightened out.
files.
So
Right.
that one actually, my 20-minute exposure there has a slight bit of a smear to it.
Yeah. At that distance, it's not too bad though, right?
Yeah.
Cool. And we got some more.
And my first experiment on the horse head, I'm really impressive. A 50 millimeter telescope can do that.
Yeah, it's a surprisingly tough object to capture. It's more dim than people realize. So very cool.
And
Another
then
dim one.
my first night I've got to go to Geneva. I just set up and took the whole time I was there, took this image, which really came out good. Rosette Nebula.
Yeah, you got some really vibrant colors going on there. That's cool.
Yeah.
And that's from Geneva. Yay. And the Helix, one of my favorites.
Yeah. I was surprised how easy that one was to take.
Mm-hmm.
A 20-minute exposure there.
Yeah, I seem to remember this one's pretty low in the sky too. So we have a bit of an advantage being in
That was
Florida.
also at the Chiefland party back in October.
Right. Very cool. Yeah, I love that object. It's like one of my favorites. It's also known as the Eye of Sauron in some circles. So
Oh,
choose your
I think I'll
favorite name.
relabel my picture there.
Cool. Thanks so much. John
Thank you.
Pinto, speaking of sea stars, what do we got?
So I've been playing around with the S30, which is a 30 millimeter scope, even smaller than the S50. And this was the sun maybe about a week ago. This was that area of the sun was doing a lot of flaring last week. The biggest area was active region 3981. So I was just happy that, it would work.
Yeah, those sunspots are no joke. And on the S30.
This is the Leo triplet. And the 30, I have a 50, but I was really been trying to see what the 30 can do, especially with this wider field. And this seemed like a perfect target for that. And I really liked it. I'm going to actually, next time we're in together in March, I actually printed this one out using Amazon Photos. And
That's right.
it came out pretty nice.
Sweet. Cool. Yeah, that one on the left is commonly called the Hamburger Galaxy, which has got to be my favorite galaxy name of everything. Very cool. And also we have M46.
Yep, another wide field bunch of targets. Got M46 in there, bottom left, M47 in the top right, and sort of you can make out in the top left that is NGC 2423. There's actually even another tiny little one, but I'm not even going to mention that. Frank, I don't know. Can you zoom in on that, especially on M46?
I can try.
I want to. You can see there's a little planetary in there.
Oh, yeah, I see it now. Yeah, right there.
Yep.
That's awesome.
And again, that was a complete surprise to me. I completely forgot there's a planetary in there. So, it's like the next day I'm just going through the pictures and say, well, let me blow it up. Because what I really wanted to see is how round the stars were. And I said, boy, that star's really round. Oh, no, that's a planetary.
Man.
It actually has a name. It's NGC 2438.
Right. Also tying back to our main presentation this evening. It's the exploding main sequence star. Awesome. Thank you so much. What do I got? So in the past couple of weeks, I've only managed to get one new image out. This is just a little chunk of the sky in the constellation Sextans, right on the celestial equator. So, I've kind of imaged a lot of the showpiece objects out there already. So I'm kind of focusing on these more obscure, more distant galaxies. These ones are about 75 million light years away, which is pretty darn far, and kind of pushing the limits of the sky quality here in Merritt Island. But I'm pretty happy with how it came out. You can see that there's definitely some interaction going on between these two. They really are that close together. It's not like some sort of optical illusion. They're messing each other up, if you will. And if you want to know their names, they're not very catchy. NGC 3169, 3166, 3165, and 3156 up in the upper right there. And I'm sure there's countless more in the background. I'm not sure if that's like a bunch of like stellar clouds around it or if that's IFN, but there's definitely some signal in the back. This represents about probably about 15 hours of total exposure time. And if you take the stars out, you can definitely see some sort of a galactic cirrus going on there. I think that's what it is, but it's interesting. I want to research more into what that's all about. All right, up next, Lech Blazak. I think you go by Luke informally. Are you on? I'm not sure. I don't. Oh, right. You can't use your mic. You're watching on a TV, so I'll introduce this for you. So these contributions are taken with a C-Star S50, which he's still learning with. And the longest light time is on this one right here, 37 minutes. The other ones are less than 20 minutes that we're going to see. He did some enhancement with the final images using the S50's own software and also using Adobe Fireworks CS5. He notes that the S50 must have focus, compass, and level set to perfection. Otherwise, even small differences will give star trails, like with the M34 and M42 images. Well, they look pretty good to me here. He says he may need more practice. He's in a Bordelate zone, so he really appreciates having access to our darker site in Geneva. Well, I think that's a pretty darn good image. So nice little Horsehead and Flame Nebula there over in Orion. And we also have this next one too. Looks like the Pleiades, so very nice capture of the blue nebulosity surrounding that little cluster there as well. And of course, everybody's favorite, the Orion Nebula, M42. So looks like another nice shot of that from a sea star. Some nice color there. And again, seeing a hint of that little buddy above it, which, if I remember right, is called the Running Man Nebula. So very cool job. And finally, the sea stars take on the Soul Nebula, or the Baby Nebula, whatever you want to call it, formerly IC 1848. This one was taken on February 9th, 2025, and is a total of 74 minutes using a C-Star S50 and also processing in Fireworks. And thank you, by the way, for not using AI tools and just using Fireworks. I've seen like some C-Star Facebook groups where people just like have these AI enhanced images that are just completely fabricated and not real. So thank you for keeping it real. And I think that's the end of the show, folks. So thanks for sticking with us. I know it was a long one, but hopefully a rewarding one. We learned a lot of good stuff about stellar formation and what's going on at the observatories down in Arizona. Learned about our own Richard Wright's new SmartEye eyepiece. That's a very exciting project. And got some really cool astrophotos and club news. So I'll see y'all next month on the 15th at the planetarium. Meanwhile, everyone, keep looking that way. I'll see you next time. Thanks, everyone. Good night.